so just to recap once more, the workshop material, everything is available on GitHub. If you go through this link, questions on Slido or in the Zoom chat, but preferably on Slido. And as I mentioned, the crucial part the best way to run this workshop is via Docker. So I will quickly show you how this can be done. But I'm also aware that this can run on multiple machines in multiple different issues. So for you, if it's not working, then I would recommend to either go through the MyBinder link. So if you scroll down to the last part, you have here the MyBinder link. This should get you to the page that I also now have open here. So if you click into it, you're directly in the same notebook that I just showed you. You have here the slides, and so everything can be done on the platform, online on MyBinder. The crucial part why the whole workshop cannot be done on MyBinder is that MyBinder only provides 1 to 2 GB of RAM. And so especially tomorrow when we use Nipype to do some pre-processing of fMRI data, we're pushing the memory requirement. And so MyBinder most certainly will crash. But if you want to explore the notebooks, if you want to explore the slides, MyBinder is certainly the way to go. And so, as I said, MyBinder is one way. There's also Jupyter NB Viewer link that brings you to a static page. So this one is just static. You cannot do anything. You cannot change anything. But it also shows you everything, all the notebooks that you can click into. So if I click in the Jupyter notebook, it will bring you to this notebook and you can explore it. In this framework, the slides don't work. So if you click on the slides, it's unfortunately not showing them in the right way. To do so, you would need to either download them from GitHub or use the MyBinder link. And so as promised, let me show you how to run the whole thing directly from Docker. So you should now see my screen. Yes. So Docker can be run on Mac and Windows. I have the Docker instruction here, how to install it under the first point. Here, Docker, the recommended setup, how you can set it up. But it also has some pointers of how to save your progress if you change your notebooks. It has some pointers if you have memory issues. Then it has some pointers for after the workshop that you might want to clean this Docker image because it can nonetheless take up to 8-9 GB of data of space on your hard drive. And so the best way, and I'm obviously on a Mac, so on a Windows it's similar. The key part is that you need to go to a terminal. You somehow need to reach a terminal. The Docker terminal, I think is possible. And what you also need is you need to make sure that Docker is running. So here I have a small icon that tells me, yes, Docker is start and running. And so what you can do, just to test if everything is set up correctly, is to, is to do something like Docker run and then hello world. This will now download a Docker image. So it didn't find this image locally, so it downloaded it quickly here. And it's already done. And now it pasted this message. So this means everything is fine. And what you can do on a Docker framework, if I make it a bit bigger, you can also do Docker images to see which images are installed. And right now I have the Hello World image installed, but I also have the workshop image installed. And here it tells me, by the way, I'm using 8.6 GB. And so I'm just exposing you quickly to this terminal view to show you that these kind of things are possible. Peer will cover them a bit more in detail in the afternoon. But to run the workshop, what you would need to do as instructed on the platform is to do something in the direction of Docker -it-rm. So we can, let me directly actually copy it from the platform here. I can run it from this URL. So here, if I do that, I can start the Docker environment. So if I do that, it opens the Docker image, it goes into it, it starts the Jupyter Notebook framework. And if I now take a new window here, if I do localhost colon 8888/3, which is the same link that you would also find on the GitHub page. So it's also highlighted here. Yeah, here. You can use this URL or you can use this URL. And if here there's the question mark token equal Pybrain mentioned, it directly gets you into the page and everything is ready. And here again, click on the program and you're inside the workshop environment. And if you don't use this token, question mark token equal Pybrain setup, if you're just running localhost because you restarted again a bit later today, if you do that, you have this password or token missing. And here you just need to type in Pybrain. And if you do that, you're also getting back to this framework. That's the short overview to hopefully get most of you to some version of this notebook, to some version of this overview. And I will quickly check if there's any message for me. So as a next step, and I hope most of you were able to set this up. As a next step, we will dive into the Python recap part. And so here are the slides, and perhaps also a pointer that if you click on one of these links, you will directly overwrite your tab. So the easiest is always just to open it with a right mouse button or just use it on your system, open it on a new tab that you get to the right location. And so let me start with the quick recap about Python and Jupyter Notebook for those who might not be too familiar with it. So Python is a high-level programming language, which is on purpose readable and has a syntax structure that should be close to well, how we speak. The goal is really to allow a very quick learning rate to get people from other programming languages like MATLAB or C++, Java, and so forth, to very quickly be able to get into Python and start coding. And also to people who are new to programming, that hopefully Python is an easy language to learn and to explore. And there are numerous tools out there, tutorials to learn Python. Last week's course was one of them. But we also summarized a few things here, and I want to briefly expose you to these different things. So in Python, if you want to save a text, for example, you can just say, okay, I have a variable text and I put it into a string, so hello world. And so there's no declaration of this needs to be a text. You can just do it as such. You can print the text and then it directly gives you back hello world. Or you can also do something a bit more natural feeling, in the sense of, is world in text? And as it is in there, yes, it is. And so there are many ways on how to use Python. The easiest is Jupyter Notebooks, and we will come back to that in just a second. But it's also possible to just use a terminal. So as I showed you before, the Docker terminal, it would also be possible to just have a terminal, run your Python code in there, have an editor on the other side, and program your pipelines and your pre-processing analysis like that. This is completely fine. If you're used to it, certainly a good way to do it. But an alternative, if you're, for example, coming from MATLAB, something that has very much a feeling of MATLAB is something called Spider. And so I can show you quickly the page of Spider. It has these kind of frameworks. So you have on the left side the folder structure, you have the code section, you can see what variables were loaded in and what the values are, and you can also use some part to have the visualization. So as such, obviously very much inspired by MATLAB and by other similar frameworks. And so if you don't want to use Jupyter Notebooks, if you don't want to use just a terminal, this Spider framework might be what you are looking for. And yeah, the third way that I recommend, especially for doing research, doing exploration of your data, of pre-processing, of creating a Nipype pipeline, for example, are Jupyter Notebooks or Jupyter Lab. And the great part is really that you can integrate code with visual outputs, with markdown text, so text that is rendered in a normal looking way. And we will also see that throughout the course and hopefully convince you that this kind of framework is a great one. And so let me actually directly jump into one of the notebooks. So here I will stop talking in about 5 minutes and let you explore these different notebooks. Again, they have content for a full day. It's really just about giving you the references for later on to go back and explore again a bit more what is NumPy, what is SciPy, and so forth. But I want to give people who are new to it the chance to get a bit familiarized with Jupyter and Python. But the best thing perhaps to start with is to show you the Jupyter part live. And so these Jupyter notebooks or Jupyter labs, they are the same framework. They allow you to, as I mentioned, to run Python code. So if we have something here, import pandas, you can import the pandas tool. And once it's ready, you can directly use functions from this tool. You can explore, you can print stuff, as I said, hello world, for example. You can have the output directly here. And so these Jupyter notebooks are really great to run Python code, but also to do visualizations. I will explain that in just a bit. But yeah, sorry, actually what you should see is something like that. So you have this toolbar here on the top that allows you to save the notebooks, to cut out the cell if you don't want it. But you also have keystrokes. So here there's a short, small button for to have all the hotkeys to directly, the shortcuts to do things. And so you can do add, insert a cell. And so insert the cell above says command mode A or command mode B. So what this is pointing to is the fact that if I'm outside, if I'm not in a cell yet, or no, let's do it the other way around. If I'm in a cell, it becomes green here. And so now I can write something. And if I execute it, so if I click here on the run button, it says it's executed. It has a execution number. It gives you the output. And now it is blue. If I click inside again, I'm again in green. And so this one is the editing mode. And if I press the escape key, I go into command mode. And so if I'm in this command mode, I can press the keyboard button A, and it just adds something above. If I put, if I use X, it deletes the cell. So if I do that here, it deletes it. And again, B for something below, A for something above. Or as I said, I can execute a cell by clicking here, run, but I can also do it with executing it directly with Shift Enter on Windows or Command Enter on a Mac. And I think Linux is also Shift Enter. So this should give you a bit of the Python framework, the Jupyter Notebook framework. And as I said also before, it allows you to write comments. So I can write something like this, and if I do it just like that, I'm still in a Python cell, and that's why it tells me, there's a syntax error, this Python command doesn't work. But if I switch here from code to markdown and execute it once more, I have it as text. And I can then also make a header out of it and so forth. So this notebook allows you to have markdown cells. It allows you to have code cells. The other two we will not cover for now. And yeah, what I would recommend is that you now, for the next 20 minutes, I would recommend everybody to explore these 7 notebooks. They surely have stuff in there that might be new to you. And then in about at 30, I will come back and recap and give you the pointers that are relevant for the next part of the workshop. You can also, of course, write me on Zoom. So Slido, again, Slido is the best chance to get an answer quickly from me. Otherwise, you can also directly write me on Zoom, and I will see how quick. So see you in 20 minutes. So I think we will continue. I will wait 2 minutes for everybody to get back. As Johan already said, on Slido, there were some good questions with respect to Docker and the Jupyter notebooks. Docker should work in 95% of the cases. Some Windows setup are a bit more to get it done. There's an issue with virtualization, which can be due to, not sure if it's older system, but system that don't allow this kind of framework. But I believe that the Docker desktop can handle that. So if you follow the link on the, let me also share the screen once more. If you follow the links on the GitHub repository under the Docker section, You have here the instruction to download, install Docker Desktop. You have some more detailed information about the Mac, Windows, and Linux system. And as mentioned before, potential issues that you might have with memory or with getting Docker to run on your system. Perhaps something to highlight on this note is that depending on how you've installed Docker, it might not be as powerful as your computer would allow or could do. So if you have, if you click on the Docker symbol on your machine, if you click on the dashboard on Mac or on the setting part on a Windows machine, if you click that, this window should pop up. And here under settings, you have many different things you can set up. But the important part is here the resources. And under the resources, you can say how many CPUs you want to allow Docker to be capable of using. By default, this one is at 2. So if you have a stronger machine, don't hesitate to ramp that up. Then some of the analysis later on will go quicker. You can allow it the amount of memory of RAM that you want it to be able to use. And you can also allow the disk image size, the space that you allow on the that can be used. So the workshop currently is about 8.5 gigabyte of size. So if this one would be too small, that could also lead to some issue of installing it or opening it the right way. Yeah, but as mentioned before, let's recap some of the Python things. So let me go back to the slides. Python has much similarity to Matplotlib. There are a few differences, but if you're coming from MATLAB, sorry, force of habit, then it should be a quick transition. But a few things perhaps to point out, and let me for that jump back into a notebook. So let's say we're here in the Python notebook. Let's just add a few cells above to show you different things I would like to highlight. The nice framework of Jupyter Notebooks of Python is that for later on, if we need to import new packages, so instead of having everything available at once in Python, you need to import them. And one famous package is NumPy. And what you can do is you can say import NumPy, and then you're able to run the mean function from NumPy, for example. But if you don't want to always type in NumPy, you can also directly import it as with a placeholder and then say, okay, now let's do the np.mean. And if I do that, it gives me an error because I didn't specify any inputs. So let's quickly add something here. And now it gives me the mean back of these 3 numbers, the average. And so sometimes you're not familiar with, or you don't remember exactly how it was written, what the name was. And so what you can do is you can write already a part of it and then just use the tabulator key. So if I press tab, it completes it. So now it added the n. If I press tab here, it will actually show me the other opportunities or possibilities of the command I was perhaps looking for. So the median as well, and some other things. And so if I say, no, I wanted the mean function, I can add these round brackets to say, okay, this is a function. And if you're not familiar anymore what exactly the input could be, what can be done is shift tab. So if I press shift tab once, I get the very brief introduction of what are the parameters that you might be able to use. So A is something, axis, and so forth. So we don't know yet what it is. But what you can do is if you press shift tab twice, so tap, it gives you something to scroll through. So this is the help page. Or you can also press 3 times, tap, or sometimes 4 times, and then it opens this whole thing in a lower section of your notebook. And so here it tells me that the NumPy function has a parameter A, a parameter axis, dtype, and it tells me here what they can be, these values. They are explained of how to use them. They have also a section about what will be returned later on. They have a section about examples. And all of these information help you to very quickly get information of your functions that you would like to use. The nice thing is this text that we have here, compute the arithmetic mean. This one is exactly the same that you would find if you would go online and go to the help page of numpy.mean. It is one-to-one here, compute the arithmetic mean. it's the same thing, the same help text, the same parameter information, the same return information, the same examples. So instead of always going to a new browser and exploring it there, you can also directly just access it within this framework. And yeah, copying it from the slides, we have different data types, strings and integers, float numbers or doubles, also in other languages. You can assign equals mean is this one the same as this one? Yes, it is true. And here as well, so in Jupyter Notebooks, always the last command that you're running is printed out here. So if I comment this part out, nothing will happen. But if I now say here just number 2, it will print number 2. If I now uncomment this one again, it will print this last statement. And these short characters will be ignored in a Jupyter framework. And so perhaps to highlight something that is different from in Python and in MATLAB, if you have a string and you do something like this, you can, for example, split it. So if I do the split, it will split these 2 words, but I can also say, now I can say, okay, of these 2 words, give me the first one. And in Python, the first one is the 0. So the first one gives me the hello, and the second one gives me the first. And so just to showcase these different things, so here we have a list. If I do type, I know that it's a list. And again, I want to expose you to different things here to quickly know later on how to find these kind of information. You can say for elements in this split, which was before this hello world. Sorry, not this one. This hello world, if I do the split command, I get here, if I do that, I loop through this one, I can say each time print this element. And so this gives me the first time hello and then second time world. And so I don't want to go too much in detail because of time, but these are a bit of the basic things of the different data types, of how to print it, how to access information of the models you want to use, how to run for loops. And if I go to slides, we also have the different types of lists. So we have lists, how to access it exactly with an index. We have lists, we have tuples or tuples, we have dictionary, and all of these have their own characteristics that I would recommend to explore in a different time point. Oh, sorry. We also have here a short pointer of how functions can be used, and something like list comprehension that will come back in later units, in later parts of the workshop. But so the other question that came also up is how to use these Jupyter notebooks without Docker, without any environment. And so there, the key point is to have Conda. Conda allows you to set up a Python environment to quickly get everything up and running for everything we show you. So all the codes that we show you here, you could just use Conda on your own machine. We are using Docker because it allows us to directly provide you with a framework, with the data, with FSL installed, with SPM installed, and so forth. But if you are working just on your own, if you just want to explore the neuroimaging ecosystem with Python, Conda should be enough for the big part. For the Nipype part, you need to also have the FSL, SPM, and other libraries installed. But for here, the big part, use Conda or their related products, Miniconda or Anaconda. But again, this pair in the afternoon will cover in much more detail. The Jupyter notebooks I've covered already, the different ways of how to interact I've mentioned, but here we have some additional pointers of when your kernel, your notebook is crashing, what to do. I will jump that as well. I want to briefly highlight these other toolboxes. So NumPy, I've just mentioned before with the numpy.mean. NumPy is really the fundamental toolbox that is almost behind everything. If you do some part of data analysis, it allows Python to be almost as quick as C++. And it's a great framework to work with data, with arrays, with matrices. And yeah, so it might not be always the case, sorry, it might not be always the case that you're aware of using NumPy, but NumPy is always there. SciPy is, of course, for scientific Python. It has some additional great tools. So if I go quickly here in the SciPy, no, sorry, this one is the NumPy, the SciPy notebook that you can access from the main overview page. It has many different sub-packages, but what I want to highlight is you can use SciPy to load MATLAB math files. You can do data interpolation, so linear interpolation between points or cubic interpolation. You can use it directly to do curve fitting. So if you have points like that, you can fit a curve through it. So there's a vast possibility with these kind of things. You can do Fourier transformation to get the main frequency of something like that. So if you do the power spectrum, you see that this frequency is most dominant in the figure above. And so SciPy, again, as NumPy, is used in the back of many tools, but you will not always be aware about them. But certainly, nonetheless, it is worth it to explore. The other tools that we will see is scikit-learn. That's the machine learning toolbox in Python that we will see just in a bit, in 5-10 minutes. And the two other notebooks, I think, that give you a broad overview of what is possible with Python is the statistics in Python. So here we have a few pointers to pandas, SciPy, so the stats model from SciPy, to stats models, or to Seaborn. And just to briefly highlight one part of stats model. So here we have the section about the stats model, where it starts, and you can use that to do statistics on your data, and you can get perhaps familiar looking outputs that tells you, for example, the OLS regression results, the intercept, the coefficient, what is the coefficient of the intercept, what is the t-value, what is the statistics on that. So stats model can be a very powerful tool to analyze your data, to do simple descriptive statistics, but so are also Seaborn and all the other toolboxes that I mentioned here. So exploring these four is certainly also a great opportunity to broaden the skill set to do statistics in Python. And the last thing that is really cool and is connected with these Jupyter notebooks is how to use different toolboxes to visualize stuff. So all of these visualizations can also be done outside of a Jupyter notebook, but the Jupyter notebook offers a really great opportunity to have this mixture between these markdown text, so these normal LaTeX-looking text box, plus having the code and having also visualization. So this one is now a plot that can be run through here directly in the notebook. If I change it, I can make it much smaller, unreasonably small. So that's the nice part of directly having an integrated visualization in this notebook. And yeah, so there, the matplotlib, it's, if I go up here again, we have the matplotlib. This one is inspired very much so by MATLAB. So it has very much similarity in color theme to what you would do in MATLAB. Seaborn is an adaptation of that. Seaborn is a great toolbox, if I click on it, for quick visualization of beautiful visualization. And for all of these toolboxes, if you go on their page and if you go to the galleries section, you can see many different plots. And if you click into these plots, you see what kind of plots could be possible and the short code that would lead to these visualizations. So exploring these toolboxes is certainly also a great way to better understand what can be done. But one thing I wanted to highlight here is, well, the Python Graph Gallery is a great tool that if you click on it, you can have many different types. So if you look for distribution, different ones, so box plots or violin plots or scatter plots or bubble plots, whatever to your heart's desire, you can click on one of them. So let's do the violin plot. If I click on it, it shows me how to do different violin plots in different libraries. Here, for example, using Seaborn. So these are all violin plots in Seaborn. Well, here we only have Seaborn, but if I click on histograms, well, they only show Seaborns. Good. But it also has examples of how to do it in MATLAB and other libraries. But the interesting part with this combination with Jupyter Notebooks is this plotly part. So if I scroll down to the very end, I wanted to show you these plots. So here in Plotly, so this is the Plotly section. Plotly allows you to have interactive figures. So for example, here, I can directly see what is this value or this value. I can also highlight that I actually want to see all values at once of these 3 ones. If I have a time series, I can zoom in. So I can say I only want to see these things. If I have something like that, I can say I want to only have this section. If it's a 3D plot, you can really interact with all of that. And so this is really cool in combination with Jupyter Notebooks. And the nice part is also if you do your whole analysis, so if you do everything, you have your code in this notebook, you comment your outputs, you comment what you have, and you have your plots, you can save that as an HTML. And if you save it as an HTML, it takes a few seconds, and you have now everything ready here in an HTML with the figures included, with the interactiveness of these plots, and you can just send that to somebody else. And so that is, I think, a very powerful way of interacting with Python, of visualizing it, doing the statistics and everything else. Let me go back to the slides. Yes, this we've covered. This as well, and we're already slightly over time, but that's no problem. I wanted to quickly take the time to allow questions, if there are. As technical questions, ideally on Slido, but if somebody would love to ask a question for everybody else, don't hesitate to do that quickly in the chat, if I can get it open. Anybody has a question? Otherwise, I will already prepare the next section. Good. Yeah. Don't hesitate to write the questions. We are on Slido. At the moment, it's only Johan, but I will try to jump in also in just a second and hopefully debug some of the setup problems that are occurring. But let's move on to this next part. Nibabel and Nilearn. So if we click on the slides, the introduction to these toolboxes is rather simple. Nibabel is really the toolbox to use neuroimaging data. So I've mentioned here it's everything you need to load and save images, but it does also much more, which you will see in just a bit. It is really the fundamental that is behind everything if you work with neuroimages. It can load the data, it can give you information about the headers, the affine matrix, the location in the space. You can use it to transform your data and save it in any kind of framework. So this we will see in the notebook in just a second. And Nilearn is built upon Nibabel. Nilearn is really the toolbox to do many great things in Python, and we will see that during the next, this day and tomorrow. It allows you to do, beautiful figures. Hopefully we will see that in just half an hour. Beautiful figures, great transformation, great data pre-processing, cleaning, exploration, and so forth. And I will summarize both of these toolboxes after you've explored them yourself. So yeah, let's do 10 minutes, about 10 minutes, where you can go through the first notebook. So you can click here, right mouse button to open it, or directly here on the Nibabel page. I recommend that you go through this notebook and then in about 10 minutes, let's say 5 past 11, let's come back and I will briefly summarize a few things. So let's continue again. I will do a quick recap on Nibabel and then we can move on to Nilearn. So let me share the screen once more. As I said, Nibabel is really in the back of everything to handle neuroimaging data. And so if we take the first notebook and just import a few of the relevant packages, so here just the Nibabel one plus a few others to plot. If we execute that, and then we for example, take a data set that is stored at this location, so I can quickly perhaps highlight that a bit more. We have a lot of different data sets stored under data. So we have actually currently in this workshop, we have 3 different ones we will use. And so here, if I do ls to list the directory, it will show me that I have here a Nifty file and a TSV file, a tabular separated file. And the nice thing with Nibabel is that you can, without any problem, just if you have the path to the file, you can load it with nb.load, And once you load it, you can see the header information. So you do print, you get all the headers information that you would also see in other toolboxes. The affine transformation matrix, the dimensions. So here we know it is 4-dimensional with this base resolutions plus 184 functional volumes with a TR, which you can see here. That's all of that is hidden in the pix dimension. So instead of reading it out here, we can also directly get these information. For example, here the image.header pix dimension, and you can extract any kind of information that you have in your nifty images with Nibabel very quickly. But the other thing that is also very nice, so if I go here, we can very quickly access the data, so that happened above, and then also just plot it. So this one is plotting as you would plot anything else in Python with matplotlib. But the framework of Nibabel has also a few nice tools that sometimes work, not always. So it is possible in a Jupyter notebook, if you say, I want to have the next visualization in a notebook, it's possible to have these kind of things to then load the data set and click through it. It is very slow and it is prone to not work so well, but it is possible to already with Nibabel to explore your data set in a rather quick way. And yeah, the other thing are really transformation. You can do it directly here. You can get the orientation of how your images were recorded. Let me rerun some things. You most likely will not interact with Nibabel a lot because everything we see here can also can be done with Nilearn, which is in the next section. But one thing that I like a lot is this nib-ls command. So I've mentioned before that we have some files here at this location. So if I do, again, just this one, it tells me that I have two files. One's a nifty, a compressed one, and one's the tabular data. And if I just now execute it with this command, here, nib-ls, it gives me some basic information about this data set. It looks now a bit not so good because it's on 2 lines, but if you would have it on in your terminal, you would see it much nicer. But let me zoom in again, highlight what the output is. So what you get is you get the name of the file, which is this part. It tells you it is saved as an integer image. So it has a dimension of bit size of 16 to encode integers. It has these 3D volume dimensions. There's 184 functional volumes. And the resolution, the pixel resolution is here mentioned here, and the TR as well. So a TR of 2.5 seconds. And so this tool I use very often to quickly explore all the data that I have. Let me add here the compressed tag that I only see the compressed files. And so here I see I have subject 1, subject 2, subject 3, and subject 7. And I see, not so clearly in this regard, but I see that they actually are all mentioning the same dimension. And so this nib-ls is a very quick way to see is the TR still as it should be, is the resolution as it should be. And so that's a really cool thing. And of course, you can also directly access the header if you want to. Sorry, not this way, there was something else. There's also many nib dash, and then you can see many other functions that you can explore. Not from the notebook, you will need to do it directly from the terminal. Yes. But now going over to the Nilearn, and I want you to have enough time to explore that. A quick reintroduction again. Nilearn is really the toolbox to do many things. As you can see, it has this nice Python snake brain logo that you also see on Nipype, that you also see on not Nibabel, on other toolboxes. But from the other side, from this logo here, you can also see that it has a lot of resemblance with scikit-learn, which is this logo here. So scikit-learn, again, is the machine learning toolbox in Python. And Nilearn was developed by a few people from scikit-learn and now the open source community. And so Nilearn, you will see in this notebook, gives you a lot of flexibility, a lot of power to do many, many amazing things. And so I think best way to to learn it is to explore this notebook. So that's now the second notebook. So that would be this one. Let's say until until 45, so about half an hour. And then in half an hour, we'll come back and I will summarize key points of this. So welcome back, everybody. I will continue with summarizing the Nilearn part for lunch. Let me share the screen once more. So there were also many good questions on Slido. Thank you very much for all the questions. I hope I've answered most, and Johan as well, but if not, don't hesitate to ask again. But let's jump into Nilearn. So Nilearn is really the tool. I hope most of you were able to get through a huge part of it. It's the tool to explore your data set. So again, let's say we are loading 2 images. So once we load an anatomical image, so T1 weighted one, and once a functional image. And so what we can do, I need to quick some computation. If we look at the data set, so we have here the T1. It is in this weird Nibabel nifty format. But if I now do shape, I can quickly get the shape of this one. Or if I do bold and shape, I get the shape of this one. And so I know the X, Y, Z dimension. And if it's 4-dimensional, I have the volume dimension. And so if I want to access only a few of them, you can use this slicer object. And that's what we did down here. So if I do just say from volume 100 on, if I do shape, again, it tells me, okay, now we only have 84 instead of the 184. So the slicer object allows you quickly to slice around. But as I've mentioned, Nilearn has so much more. And so you can very quickly use from Nilearn the image package, or here abbreviated as NLI. You can create the mean image of the bolt. So you have this functional image all here. You do quickly say, give me the mean of it, and it will create the mean over all the volumes. You can plot them with the plotting tool. So you can say view the image, and you can quickly investigate and look at your mean image. You can resample very quickly. So if you have the bold image and the T1, the anatomical image, they don't have the same resolution. So this is the resolution of the functional image. This is the spatial resolution of the anatomical image. And you can just say, please resample the T1 image to the same resolution, to the same specs of the mean image. And so the result is the resampled T1 image. You can again plot these two. So this one was the original one, and here we have the resampled one. So as you see, Nilearn allows you to very quickly to flip back and forth, to resample them, to do something like the smoothing approach. For example, here you can say smooth, and here I only smooth the mean image so that it's quicker. You can say smooth it once with 1 millimeter, once with 6 millimeter, smoothing kernel, once with 11 millimeters. So you can give the image, so here the mean image, as being a nifty image, but it very quickly transforms, gets the data out of it, transforms it, puts it back into a nifty image, and it has it here. The nice part is you can now also, as we saw in other instances, you can also save the file. I will need to quickly recap that later, sorry. But you can also clean the image. And these things that I'm showing here are just to show you the possibilities of Nilearn. It's by no means intended that this is the right way of analyzing fMRI data. The proper pre-processing of fMRI data we will also address tomorrow a bit more, but it's not meant that you do the whole thing with Nilearn. For example, something like realignment or motion correction cannot be done in Nilearn. For this, you would need AFNI, FSL, SPM, or any other toolbox. But Nilearn allows you to do many steps in between, or many exploration of your data very quickly. And so the cleaning function here that can be used is a function where you can take a functional image, you can detrend it. So if you have an uptrend in the images, you can take this uptrend out. You can standardize it. So where the values might have been before, somewhere around 800, you can make them at the mean of 0 with a standard deviation of 1. But you could also, with this function directly, you can explore also other things, like you can set a low pass value, a high pass value. So you can directly filter these functional images directly from the bold. So if this bold here, back up here, let's say you don't even need to load it to a certain degree. You can just take the location. You can say this one is my image at this location. You feed it in here, and it does everything at once. So it loads the data, puts it in the right framework, it detrends it, it standardizes it, and so forth. And you can use many other functionalities that Nilearn has. Thresholding, you can say, only show me the 5% most active or highest value voxels, so that I can see a bit where are the hotspots. For example, if you're looking at a statistical map, here the mean doesn't make so much sense, but if you have a statistical map, you can say only show me the 5% of the top voxels that are active. You can say extract all regions, extract all clusters in the brain where the regions are at least 1,000. I think this one is millimeters, cubic meters. Sorry. So the minimum region size here is in cubic millimeters. And so you can say only give me voxels back that have this bigger extent, the clusters that have at least a certain extent. You can very quickly run ICA, explore the ICA, run it, visualize the first, second, third, fourth component, see where is the load of these components. So if you have it more on the side, there might be an indication that it's motion artifacts. And then when you know that it's a motion artifact, you can also look at the time course throughout the image. So these will be now throughout the 186 volumes. You can see with this kind of things, as you would do with FSL or any other tool that you use to do an ICA, you can quickly extract the principal component, the independent components, and get more of a feeling of what it is, where the components are, how they are expressed within the brain. Dictionary learning is an alternative to ICA that shows that it has a bit more strength in some parts. So that's where I interrupted the code. Plot a few of them. So dictionary learning, you would need to read up more on the Nilearn homepage that explains a bit more detail what it is, and also points to the right paper. But it tries to consider the spatial dimension of the brain, whereas the ICA only looks for components in general. The dictionary learning looks more for components that are also connected and positive. So it is also one way to perhaps explore your functional images and to find perhaps some noise components and also to handle them. And as I've mentioned, so Nilearn has all of these functionality, but the other part that is also really strong are the plotting. The plotting functionalities. So if I run all of these cells as well, I apologize. You can load your data. You can use something that is called the glass brain. So in this glass brain, you have the broad outline of the brain. This is of course the MRI template brain, template space. So to plot it here, you first need to make sure that your functional images, your t-statistic or anything else, that it is already normalized to the MRI space. But you can then have these nice overview plots to see from the top, from the right side. So this one is only the right hemisphere, only the left hemisphere, or from the back. And it really is the view throughout the brain. So this cluster here is obviously this one as it is this one. And so these glass brains are nice plots that allow you to get a big overview. You can use slicers to see different slices of the brain. You can see orthogonal views and so forth. So you have a lot of flexibility of plotting your data, plotting it with different color bars, plotting it with different setups, plotting ROIs, regions of interest, atlases. To your heart's desire, you have really a great toolbox with Nilearn to get many great visualizations. The etches, I apologize, this one didn't work well in this framework, but I wanted to highlight a bit more what it could be used. So, for example, a toolbox called fMRI Prep, which we will see more in the afternoon, uses this to plot the anatomical image. and to plot the brain mask, so the binary mask of the brain, of the extracted brain, and plots then only the edges on top of these of the brain to indicate where the brain was extracted from. So this is also a great plot to quickly give you overlay two things where you only want to see the outline. But the really cool part of Nilearn is also the capability of 3D plotting, so plotting on the surface. And here it's important to mention that these surface plots, without having the actual surface reconstruction from FreeSurfer, this is only an estimation and only a projection of how your functional images would be projected on the cortex. But if your data is in MRI space, is normalized to the MRI template, you could use Nilearn, and you could use the plotting functions to directly project your functional image onto the surface and create plots like this. So this is the inflated view of the surface, or the pile view of the surface. But Nilearn, as with or ortho view of exploring the image interactively, it also gives you the capability of projecting your data. This is just the mean image or the localized image that doesn't make sense. I didn't threshold it at all, but you can quickly project your data onto the surface, explore it, switch between different visualizations, directly go to different view places, switch hemispheres. So this is really the great part of Nilearn, this interactiveness, the way of plotting something very quickly, like here, or like in the glass brain. And perhaps to showcase another example where in a toolbox that I've written, fMRI flows, there I've also used to create informative figures once the data was pre-processed. And so, for example, everything done with Nilearn, I've created this figure, sorry, actually here, where that didn't work, where I've also color-coded the segmentation, gray matter, white matter, CSF, and so forth, or indicated in a similar way as with the edge plot where the extracted brain is. And so these kind of functionality, these kind of plotting can give you a great tool to use Nilearn to visualize what outcomes you received from the pre-processing, and to make sure that as a quality control tool, to make sure that you're pre-processing it, that your analysis was doing the right thing and not suddenly cut out too much or not enough of the brain. I think that is what we wanted to see for the morning. So just to quickest recap, or let me actually go back to the slides. On the slides, I still had some summary of Nibabel as well. So it can really be used to load the images, to get the information of the affine matrix, get the data into your framework. You could also from here save it in a mat file if you need to move it somewhere else in a MATLAB code. And the Nilearn really has all of these amazing functionalities. Perhaps let's just do one small thing here. So you have the mean image, the resample, the smoothing, and so forth, the cleaning. But just to highlight really the flexibility and the strength of Nilearn, let's take the bold image here. So just to recap, this was in a volume with 179 volumes. And so what you can do is also, if I take from Nilearn, from Nilearn image, let's take directly the code that I have up here. So then NII command. If I do something like the math command, math image, I can say here, I want an image, and from this image, I want to have the mean. Let's go one step back. If I have this bold image, I can say, okay, give me the data. And so this one is now the data. I can quickly extract it, and now I have it as much in Python as it can be. It is a NumPy array. And so here I can say, give me the mean of this data. If I just do that, it gives me the average of everything. If I say, no, please collapse over the last dimension, which is the functional here, then it gives me a matrix back with this dimension. But in this case, it's really just a data matrix. There's nothing connected to neuroimaging, nothing connected to the brain space, to the MRI space, or so forth. But what I can use is I can use this NumPy command and use this one directly with this Nilearn math image command. I can copy paste it in here. I can say this is my image. I then specify here that my image, so this one is the same name that I have here. I can say this one is actually the bold image. And now if I say that, if I execute it, I get the new image and I have the shape. This seems reasonably quick, but what I can then say is actually I want to have everything, only the absolute values, and I want only the values that are above a certain value, let's say above 100. And so this one gives me now the same dimension, but if I do now the plotting function, plotting the statistical map, I can plot it here. I can see a visualization of something weird, and this is now due to the fact that, well, yeah, this is due to something else. I will skip that here. It takes too long to dive into that. But what I wanted to highlight at this place is really that you can very quickly use this math command. And now here everything is in the 2200 regions. You can subtract, let's say 2000 from it, and your volumes have now all the value of 2000 less. And now it's negative actually, because I pushed many of these voxels to the negative space. But you can also say divided and so forth. So it's really, this math image gives you everything as kind of a calculator into your hand. So now the space is from 0 to 1.1. And so this is a very, very strong tool that you can use. And as mentioned before, this one is directly already an image that you can directly save again on your machine and use it as a nifty image in other contexts. So to recap, we had a short overview of the workshop, some quick recap of the Python framework. Hopefully in the meantime, most of you were able to also get the Conda, the Docker environment running. And then we looked into the Nibabel and Nilearn part. Just to summarize this, the issue with Docker that also Peer will cover in the afternoon, I want to highlight briefly again that everything that we use in this workshop, so everything that you also find on the GitHub repo, so the workshop can be downloaded from this GitHub repo, the content. All of the notebooks are in here. They are here, stored here. The slides are here. The Nipype tutorial for tomorrow is here. And we are using Docker for this framework to guarantee that all of you have already within this Docker image FSL installed, SPM installed, and so forth. For your own analysis, if you're not interested in FSL and the other things, you can directly also just install the Python environment with this Conda approach, or even without Conda if you're familiar with it. And if you just want to explore the workshop, you can use the MyBinder version. But this MyBinder version will not work as much in the afternoon, and certainly not tomorrow. So the best thing is to use the Docker environment. And I'm happy to, if the people who still have issues, they can write me a message, and I'm happy to look into that with them in a one-on-one.
And now we're going to continue with how to set up your system using Conda and Docker. And then after this session, I think we should have a short break after each session, just like a 5-minute natural break kind of stuff. Get a bit of water, get some coffee and whatnot. After that, we're going to continue with function connectivity and machine learning, focusing on function connectivity. And we're going to do that with Nilearn and scikit-learn, respectively. And after another short break, we're going to talk a bit about, we termed it innovations in neuroimaging tools, but you could also phrase it differently. It's basically about presenting you some things that are either already established in neuroimaging, but are comparably new, and new things that are already in development, but maybe not as widely established as, let's say, PyBIDS, for example. So it's about presenting you some toolboxes you can do cool analysis with in a very easy and Pythonic way, or presenting you some nice platforms that are out there that you might not be aware of yet. And this is really, I think Michael already outlined that in the beginning, our whole take with these workshops. We are aware, and I hope you are too, is within a 2-day workshop, it's not at all enough time to get proficient in any of these tools. It's basically presenting you a way into this field of Python, neuroimaging, and everything that it's about, to basically give you an idea. Because when you start without these kind of things, it just keeps getting bigger and bigger and bigger, and you just really lose track of things because there are so many things out there, and it's not very easy to comprehend at first how to integrate with each other. And the innovations in neuroimaging tools basically is like following that idea. So, but enough said about that. We're going to get to that ASAP, and we're going to start with Conda and Docker now. So we talk about virtualization. Let me just get turn off my video so that to keep some bandwidth. Okay, can you still hear me?
Mm-hmm.
Awesome, good. Because like the tab disappeared for me. I'm never getting used to Zoom, I think. Okay, so Michael told me that, or what I saw also in the Slido deck, is that some people had some questions about this whole virtualization topic. Unfortunately, within this workshop, we cannot devote a lot of time to it, even though it's one of the central techniques, as Michael already outlined. So within this presentation, we're going to have some links for like follow-up tutorials and workshops, also like introduction workshops, like a bit more full-fledged material. As Michael already outlined as well, it might not sound so related to neuroimaging and Python and neuroimaging analysis, but it's really a central tool. And it got to that within the last, I would say, 5 years, where virtualization, let it be Python virtualization or container virtualization, and we're going to get through that in a minute, is a thing that tremendously helps you regarding a lot of aspects of your data analysis workflow. Sorry, let's see. Yeah, there we go. So our outline for this short presentation is that we're going to talk about your learning objectives, the requirements you need to have on your system you're currently running on, give you a basic introduction of these things, some tools, and sometimes we draw exercises, but I think in the interest of time today, we will keep it at this and get you to the examples that we have in there. So what we're going to talk about is, why do we use virtualization, and what are the various types of virtualization? How can we use virtual environments and Conda, and how can we use Docker or another container software such as Singularity? And the requirements for you should have on your computer is basically having virtual env, pip, Conda, or Docker. And what you should be able to somewhat utilize is the shell or terminal. So I'm aware that all of this is not very Windows OS friendly, but let me tell you, we did these workshops a lot, and we usually manage to get everyone on track. And it's possible to use all of these tools within Windows, even though it's not as straightforward as on Unix-based systems such as Linux or Mac OS. So virtualization technologies basically focus on two main points. The first is isolating your computing environment. That is, pack everything together that is your computing environment and isolate it from all other dependencies. And with that, to provide a mechanism to encapsulate the environment in a self-contained unit that can run anywhere. So isolating your environment and isolating it in a way where we can share it with other people, and you can run it at different operating systems, at different machines. And you might ask, why do you need virtualization at all? The first main point here is science reproducibility. Each project, and I think you're very aware of that, in your lab, in your institute, depends on a complex software environment where it's basically going around different levels. It's, I'm sorry. The first thing, of course, is your operating system you're running on. As outlined briefly before, is a major difference between Windows and any Unix-based operating system. Then, of course, also your drivers are important. And then we go even further into software dependencies, such as Python. There you have, again, different Python modules and versions. You have MATLAB, you have R, and you have other libraries you might use. And what we try to avoid when using virtualization is basically things like the computer I used was shut down a year ago and I can't rerun the result in the analysis from my publication, which might become a problem if a reviewer asks you to do so. And looking at, I don't know if PIs are here right now, but here I would look at the PIs. They could say, or quite often do actually, the analysis run by my students. I have no idea where and how, and I have no means to replicate them or rerun them again. Another important point is collaboration with your colleagues, let it be in your lab, institute, or worldwide. Sharing your code or using a repository might not be enough. Don't get me wrong. I think it's fantastic that more and more people share the code they use within their publication or software they developed in a repository. But quite often, just doing that is just not enough. And what we try to avoid is things like, I forget to mention that you have to use CLang, GTC never worked for me. A classic one is also, I don't see any reason why it shouldn't work on Windows, but it actually means, at least in my case, I have no idea about Windows, but I won't say. Or the all-time favorite, oh, it works on my computer. And I think most of you heard one of these at some point in their academic life. And also an important point is we have the freedom to experiment. I think also the majority of you went to these days where you just try to install one software for like hours. And you start with one software and then it needs another 3 softwares. They need another 20 softwares. And you just spend the whole day trying to install that one piece of software. And in the end, it basically just works. And you spend another, like, I don't know how many days and hours on it. And what we try to avoid here is basically, I just want to under the last 5 hours or even days of my life, trying to get this thing to run. And there are different tools that can help us achieving this goal, where these are organized along different types of virtualization. And basically you have 3 main types. The first is pure Conda virtualization, where you have virtual environments and Conda environments. Then you have containers such as Docker and Singularity. And the last one, virtual machines such as VirtualBox, VMware, but also AWS and Google Compute Engines. And a while back, I think, as far as I can remember, virtual machines were actually a bigger thing, like in workshops, but also for different tools and software. But then it got actually taken over by Python virtualization and containers. And the main ideas, again, are we're going to isolate our computing environment. We allow the reconstruction of our computing environments and the sharing of our computing environments. And this is just like a very outline graphical depiction of all these things that go on in your machine you might not be aware about. But you have your isolation in depth at this end of the spectrum, where it's basically your application, a package compiled software that runs with self-contained in itself, and you don't need anything else. And then the further down you go, the more you go to like what we call the bare metal version of things. And the more you go down, the more these virtualization layers change and the things you need to include to make them run. And to give you a brief idea about virtualization in Python first, using environments and virtual environments, VN and Conda. And the basic idea here is that you keep the dependencies required by different projects in separate places. So you don't have one Python installation on your machine with which you do all of your things, because most likely that won't be possible. Let's say you're working on 3 projects, there's a fair chance one project will need a version of a software that is not compatible with another version of a software, and then things start to break down for one of the projects at least. So what you can do with VN and Conda is actually you can work with specific versions of libraries or even Python itself without affecting objects. You can have as many Python installation as you want on your machine in parallel. I'm not saying you should though, but I'm not saying you should have 20 or more, but for each given project, you can definitely have one virtualized Python environment where you can, an example, have, let's say, Python 3.6 or Python 3.4, and then specific versions depending on the project you're working on. With VN, it is basically a virtual environment manager for Python 3.4 and up, and it's actually pre-installed with Python once you get that on your machine. Conda, you need to get extra on top of that, depending where you got your Python from, but most likely you will need to do that. And it's a package manager and an environment manager. So it actually combines the capabilities of virtualenv, a virtualization manager, and a package manager such as pip. It's another one you might know. So you can both create environments and install and manage package within them. And Conda is quickly installed with the mini Conda thing. There's also the full-fledged Anaconda thing, which comes with a bunch more things like Jupyter and its own like navigation manager and window. But if you don't need a lot of like graphic user interface on things already pre-compiled and installed, I would definitely recommend going with mini Conda because it's just more slick and you can go from there as well. And to give you a brief idea on how to use Conda, because as I said, unfortunately, we cannot go through all of these things. It's a command line interface. So there's no graphic user interface for that, except if you want to use the full-fledged Anaconda thing, that's also possible there. But just for the minute, let's go with these things here. So for example, just creating a new Python environment with Python 3.6 and NumPy scipher.matplotlib, this is all you need to do. It's just Conda create, then the name of your Python environment, the Python version you want to have, and the Python packages you want to install. But you could also install different, so this will just install the latest packages of NumPy scipher.matplotlib. But you could also specify specific dedicated versions depending on those that you need. And that's all it takes. And then we'll create a new separate Python environment, which you then can use with all these versions of the modules. You can also install a new environment from a YAML file or from a requirements file. This is what you quite often can see in GitHub repositories. If you will have like an environment.yaml, it's a YAML file, or like a requirements.txt, and you can use also these things to create Conda environments. You can export a given environment if you want to share it with other people for your analysis, and you can source activate or source deactivate. And now, depending on the Conda version, it's also Conda activate or Conda deactivate your environment. And then basically activate your environment. And from that point in time, you are within your environment. So with the Python version, all the modules change to this new environment. And what I would recommend here, as I said before, I know it's a lot and a very fast pace, but if you want to start with these things, just start using Conda. Like for all of these things, just start using it, playing around with it. If you have a project to start working on or in your early phase, definitely try to set up an Conda environment for that and work within this environment for the whole duration of your project. And briefly going over to containers, and here we will focus on Docker, but most things we're going to say here are also comparable in a singularity. Docker is the leading software container platform for the majority of things. It's actually an open source project, and it runs on Linux, macOS, and Windows. Again, Windows is a bit more difficult, but it's definitely possible to get Docker to run there. The basic idea of containers is that they share the host system kernel with other containers, and each container gets its own isolated user space. And within there, you only create binaries and libraries from scratch. And therefore, containers are very lightweight and fast to set up. So if you think about the Python environments we just talked about, this is basically bringing this idea of virtualization of environments to the next level, also in creating things that are out of scope of pure Python virtualization. And if you have Docker running on your system, you can briefly test it with Docker run hello world and as Python environments like venv and Conda. It's all like a command line interface, so there's no graphical user interface for that. We put in some links here to interesting tutorials and blog posts regarding Docker containers, how to understand them, how to use them, that go a bit more into depth. Just to briefly talk about, again, these different binaries, libraries, and this more IT things here, because I think it's important to at least to a certain extent understand what's going on so you can grasp why these things are useful and important. So, and here we're going to make the differentiation between virtual machines that you might be more familiar with and containers. So in virtual machines, the idea is basically to emulate the whole computer system, that is software and hardware, and they run on top of a physical machine using a hypervisor layer. And the hypervisor in turn shares and manages the hardware of the host and executes the guest operating system. And the guest machines are completely isolated and have dedicated resources. But this is what you can see here. You have your infrastructure. It could be your laptop. It could be your server from your institute or lab. It could be some cloud system. Within there, you have your host operating system, let's say macOS or Windows. On top of that, you have your hypervisor layer. And this layer here enables all these different guest operating systems. So you could have, let's stick with Mac for the moment here. You have your Mac OS host operating system on your MacBook, let's say. And then you could run an Ubuntu 16.4 and Ubuntu 16.8 or like another Fedora or whatever Linux version. And you could even run a Windows on your machine. So you could have 3 or more different operating systems on the same machine. The problem with virtual machines is that, as said before, everything is emulated, the whole computer system, everything is created from scratch. So you have your guest operating system, one, then within you have your binaries libraries and your application. And it's the same for every guest or system you might have. Now, going to Docker or like other container structures, the idea is a different one. Here, as said before, you share the host kernel with our containers. Therefore, it's also called kernel level virtualization, where again, each container compared to virtual machine gets its own isolated user space, but you only create binaries and libraries from scratch. And therefore, the containers are much more lightweighted and faster to set up than virtual machines. So again, you have your infrastructure, it could be your laptop, server system, or the cloud. You have your operating system on it, and then you have the small layer that is not the hypervisor, but the Docker engine. Spoiler alert, in Windows and macOS, it actually uses like a minimal hypervisor layer as well because of how these things are set up. But instead of emulating the whole guest operating system, you just use binaries, libraries, and then within that, your application. And it's even possible because these things are in so-called layers, as you can see them here, that these layers can be shared between different containers. So they also are more or less storage space friendly, depending on how you use them, of course. And why is this so great? A Docker container or Singularity container, basically every container thing you might use, is a closed environment that will use the exact same software versions, drivers, and independent from the system it runs on. So you can basically rerun your analysis from like 2 years ago if you have a container in almost the exact same style and setup you did back then. It's some version of, let's say, it's the IT or like computing infrastructure equivalent of a small time travel, I would say. But be aware that it's not an entire encapsulation or an entire timestamp thing, because containers need access to your machine, as said before. So they need access to your resources, your working memory, your CPUs, and what have you. So if these things change to a certain extent, which might be an update or different software version, different libraries in there, chances are these changes are also reflected in the container. So there's also like a grain of salt there. The cool thing is when you work with images, there's this thing called the Docker Hub, and that is a free repository to share Docker images. So let's see if I can go there. Yes. So in here, so this is, for example, my Docker Hub with all the Docker images I have and work with. But let's go with a more classic and famous one, which is the fMRI prep image from the PyBIDS lab. And as you can get some information from the images, you can get the different builds, you can get the different versions of the image, the different tags, as you can see here. And when you have a look at that, the fMRI prep Docker image to this day was downloaded over 100,000 times. So it's definitely a technology that is being used and getting more and more used. And depending on if you're an organization or private research or whatever, you can upload images there and you can share them. There is little to none limitation when it comes to space of images, but unfortunately, just recently, Docker introduced a limitation on the absolute amount of time you can have images on Docker Hub. So if your image is not being pulled within 6 months or for 6 months, Docker will delete it because they have to start reducing basically the storage space. Because for like 5 years now, everyone, Michael and myself included, just uploaded basically all the Docker images, and therefore a lot of space got lost, and they need to somewhat restrict it now, I think. So that's what in there. But there's already a lot of people that created some nice tools that automatically pull a Docker container each week to just prevent Docker from deleting it. So that's also no problem. Another cool thing that's out there is called NeuroDocker, and we can also go through that in the innovation slides later. But it's basically an easy and quick way to generate custom Docker images for your neuroimaging environment. So you basically can create containers as you can create virtual environments in Python, and then do all your analysis within these containers. Or if you have a publication and want to make the analysis reproducible, you can just share a Docker image or another container with your publication, so people can download that and can rerun the analysis, which is pretty cool. Or let's say you developed a cool pipeline, a cool software package, want to save people the hassle of installing all of these things. Or for example, to make the Windows example again, you use some software that is just not compatible with Windows, let's say FSL or FreeServer. You can just create a container and make it possible for people within the Windows operating system to run these tools as well. And to just give you a brief idea how cool NeuroDocker is with just this little thing. So NeuroDocker in itself, sorry, I forgot to tell you that. NeuroDocker in itself is a Docker container. So a Docker container to make other containers. And to use this as you would use any other Docker container, and to create a container you can ship and export and make people use it that has ANS, FSL, SPM12, an entire Python virtualization environment, all in there. All you need to do is this. So this gets you the full-fledged container that is able to run all of the software, including the bigger ones as ANS, FSL, SPM12, but also has the Python environment things you can use. And this is just a very, very brief, simple example. You can go much more detailed and fancy and wild. Sorry, just to give you an example of how you would interact with Docker. If you want to download a Docker container, an existing one is on Docker Hub, all you need to do is Docker pull, and then whatever the name of the Docker container is, or the ID of the person that is hosting it on Docker Hub, and it automatically downloads it for you, and it's ready to run. You can list the images you have using Docker images. You can remove them as well. So there's a lot of things you can do in terms of managing and optimizing the usage of Docker. You can run them in an automated way, in an interactive way, so that you, comparable to Python environments, basically go into the container and work within that environment, do your thing, and then go out again. You can list running containers, removing instance. So this is all going a bit more into depth here. A crucial part is that if you want to work with files inside a Docker container or any other container, usually they are closed. That's why I call it container. So you need to open, let's say, one door or gate of the container to be able to get information in and out. And most likely for you, this will be some sort of neuroimaging or other data. So what you need to do there in Docker is to basically mount a folder. That's how it's called, a mount a path. To create a binding between your host operating system to the guest operating system inside the container. So that, for example, let's say you have a neuroimaging data set that you want to analyze within the container, you would have to make that data set available inside the container. So you mount it. And then within the container, once you're there, you can work with the data, and then everything that you do and these things are saved outside the container in your guest and your host operating system. And you can even there define different modes. So for example, if you don't want to allow data to actually be changed, you can set, okay, this is going to be read only from the beginning. So you can see the data, but not actively change it. And if you want to change it, you want to compute some derivatives, those have to be stored somewhere else. And there you can mount as many paths as you want. So you could mount one path for data input, one for output, one for, let's say, some license files you might use, for example, in FreeServer. That's all possible. And all of these things are a bit more covered. And with that, I mean, they are covered in a lot of detail in one-day workshop that is focusing on Docker we set up. And there's a session from this year's Montreal Brainiac School, which is like a summer school we do here. That is like a 3-hour session going through a neuroimaging application example using different virtualization types, such as Python virtualization and container virtualization, where you get more information on how to actually run these things. I'm going to end with a quick comparison between Docker and Singularity, because this is very important. The problem with Docker is it can and will easily escalate privileges, because you need to be effectively treated as a root user on the host system. And of course, this is usually not supported by administrators from HPC centers. So not sure if anyone from the infrastructure gang is here in this call, but they, I guess, would say this as well. If you provide even a few users with root access on an HPC, you can count the seconds or maybe minutes, but not more, till things start to fall apart, because this is just not meant. And therefore, most HPC centers don't allow the usage of Docker containers. However, another thing kicks in, which is called Singularity, which is not the whatever cosmic thing we can maybe never understand, but it's basically it's the server version of a container. So it's a container solution specifically created for scientific and application-driven workloads. And as far as I know, most existing and traditional HPC resources support Singularity container, because you don't need those escalated privileges to run them. As a user inside a Singularity container is the same user as outside the container. The only time you ever need root privileges when it comes to Singularity is when you set the container up. So at some point in time, you might need to ask some person from your HPC to set up a certain container, but that's it. And then you can rerun and use this container as you want. And this is the same for everyone else on the HPC, basically. The cool thing is you can actually use Singularity to run and modify existing Docker containers, so you don't have to rebuild a Singularity container from scratch. And in its whole command line interface, it basically works like Docker. The thing is that Singularity is best supported on Unix-based operating systems, and with that I mean Linux-based operating systems. So this is cool for HPCs because they usually run some sort of Linux system. You can also use it on Mac OS, but there you need to run a minimal virtual machine. Singularity is currently working on making that more like a native support, and I think with the newest beta, you can actually run it on OS X. And on Windows, as far as I know, please, if anyone knows more, correct me if I'm wrong, I think it's not possible right now to run on Windows. Regarding Singularity, we have also links to other tutorials and a quick presentation for our good friend Satra Josh. And I think, yeah, you also have these slides in the workshop material, so you can definitely check those links out if you're more interested into that. And with that, I'm done for this part, and I'm happy to answer questions. Now we're actually going back to neuroimaging. And we're going to take it a bit to the next level, where Michael showed you basic file handling and interaction with Nibabel and Nilearn, which already doing an amazing job of doing a lot of things. We're going to go through another classic of today's neuroscience, maybe one of the most prominent topics these days. And this is functional connectivity of neuroimaging data. And if you have your program notebook open, we are now in the section here, function connectivity and machine learning. I'm sorry, and if you click on this link here, function connectivity with Nilearn. Oh no, I'm not showing my screen, so I can say a lot of things and you don't see them. I'm very sorry. This is the thing with Zoom, right? There we go. Sorry for that. If you click on this link here, function connectivity with Nilearn, you should see this notebook opening up. And I'm gonna stop my video again. And basically what this notebook will do is show you a few basic examples of how to do a function connectivity analysis and resting state data using the Nilearn library. And we are basically covering the analysis steps or the processing steps you would do in a classic function connectivity analysis. That is, how to extract time series and how to build a function connectome, how to generate single subject maps of seed to voxel correlations, how to generate single subject maps of seed to seed correlations, and then also go a bit into the other end of function connectivity analysis, where we do group analysis of resting state fMRI with ICA and canonical ICA. So how to derive components from your signal. And as done before in the Python sections, basically what we will do is that I think we have this whole afternoon session right now is 1.5 hours, and we're going to split it in half. So we have 45 minutes for this and 45 minutes for the next session. And I would say take 35 minutes starting now, going through the notebook yourself. And then we're going to do a recap together, addressing questions and important points from our perspective. If you have any questions, please ask them on Slido, and we will try our best to help you there. And with a very calm and hopefully welcoming voice, I think we are at the end of the 45 minutes, as far as I know. Chances are you did not get through the entire notebook because it's a lot we show you there. Chances are you just want to read a bit more through or try different things. That's all good. As outlined before, you have all the materials on your machine. If it's running now, it will run later as well. So if you want to go through these things in more detail again or try different things out, it's no problem. No problem, seriously, if you're not got through the entire notebook. While talking about that, we got a question on the Slido asking about or saying that these things run slowly on the person's local machine. And this is the thing I unfortunately forgot to mention. I'm sorry for that. The tutorials we're going to do now, or like within the next few sessions and also tomorrow, they will require a bit more resources from your machine. So it's not as simply as the Nibabel and Nilearn things you did before. It's the processes are a bit more computational heavy. And there's actually a way that's also outlined in the Slido answers, I hope. Here, I posted also a link. So it's possible to change the resources your container runs with. So it's possible to set a certain amount of gigabytes of RAM or CPUs and swap memory and all of these things. So if you have the means, that is, if your machine has 8 gigabytes of RAM or more, and at least 4 CPUs or what have you, you can definitely try to bump these things up so that your container runs with more resources and can execute these things more like faster. So you can either change those things in the Docker settings, depending on your operating system, or you can also change it or directly indicate it when starting your container. And this really depends on the operating system you have, your installation. And I shared a link in the Slido to a Stack Overflow question where this is shown with an example. And if you have further questions regarding that, just let us know, please. And now to go through the function connectivity and resting data notebook. As said before, it is intended to show you the basic steps you would need to perform or that are usually performed in this sort of analysis. So at the beginning, we just check our data that we have in our data set, it's a few subjects here, and as you can see, it's not a lot of data in terms of like how long the session was, but it's intended to show you how these things work. Therefore, we try to keep it short. We also have our regressors, which you computed during the pre-processing of the data. So Nilearn does not a lot of pre-processing in these kind of sense. You can definitely work with images as shown in the other Nilearn tutorial before. For example, the clean image the functionality and stuff like that. But this also requires that the pre-processing is done somewhere. This could be any pipeline you might use, let it be SPM, AFNI, FSL, could also be fMRI prep, one of these things. And then we just indicate our subjects we want to analyze and lists to our confines and imaging files. And then basically we're already good to go to extract time series to build a functional connectome. And what we're going to use here is a brain parcellation at first. And we're going to use, in this example, the heterodox versus atlas. And as you can see, this is included in your FSL installation of the container, but you could also use Nilearn to directly download this atlas. This atlas has a bunch of different labels, and as far as I remember, I think the heterodox atlas comes from anatomical structures and cytokeratic maps, so it's not related to function. And what we can do once we have the data, we can define a nifty labels masker, a Nilearn input data method, where we basically tell this object, this function, that we want to extract the time series from voxels that fall within these labels and regions. And we can also already indicate that we want to standardize the signal while extracting. And we can also, for example, include a detraining option in here. The Nilearn input data methods are very on top of these things when it comes to that. And once we have set it up, everything we need to do, for example, here on the first subject, we just fit it. So we set it up and then we fit it to our data. And directly during fitting, we can include the confounds so that they are automatically regressed out while extracting the data. So all of this, is, as you can see, is very convenient. Everything you need to have is an atlas, your files, that is an imaging file, and the confounds. You set up your masker, you apply it, and basically then you're already ready to go and compute the correlation metrics, for which we're going to use the Nilearn connectome class and the connectivity measure function, where you can define a certain measure you want to compute the correlation, the connectivity metrics with. It could be the correlation, it could also be a partial correlation. Nilearn also has the functionality for a thing called the tangent space, which effectively combines correlation and partial correlation. And then we fit that on our extracted time series from the nifty labels masker. And with that, you already computed your first functional connectome with Nilearn. It's easy as that. And then we can just simply plot it again with Nilearn functionality. That is the plot matrix function. And here we can define the labels so that we see the labels from the atlas. We can define thresholds. We can reorder it so that regions that are more correlated with one another are closer in proximity. And you can define like other things with this function as well, which not show you right now here. And we can also see, okay, yeah, there's some stuff going on definitely here. It's like some visual regions, lateral occipital regions, and some bigger clusters right here. So, and an important thing, if you do functional connectivity analysis or connectome analysis, you know that confounds are very important. But just to stress this, and in case you don't know, we also included an example where we basically redo the computation as before, but not include confounds. So we just apply our masker, we fitted our correlation measure, and then plot our function again. As you can see here, it's drastically different. So this is without confounds, and this is with confounds included. So here we can actually see some sort of structure between regions. Without confounds, however, basically everything is correlated with everything, and this is not very helpful. Please be sure where confounds are important. To give you an idea how feasible and flexible these things are, we can do the same thing using a probabilistic atlas. So instead of like a brain parcellation as done before based on anatomical features. We now use a probabilistic atlas that was derived from functional data, and we use the MSDL atlas here. So we just get our atlas that we included in the container already, but you could also, again, download it with Nilearn. And then because it's a larger atlas, it has a lot of regions, we just want to stick to a few of them, and we're going to use the classic default mode network nodes for all y'all default mode people out there. And then we just extract those regions, we plot it, see, okay, looks about right, we can use that. And then we can do the same steps as before. Importantly, we now have to use a different input method, which is not Nifty labels masker, because we changed the type of atlas and parcellation we use. So now we use the Nifty maps masker, but everything else works as before. So you can standardize or detrend, what have you. Again, as before, we fit our masker to our files, again, the first subject, and then based on the outcome, we apply our correlation measure and plot it. But before we do that, we're just gonna get our labels, and here right now, the labels are not included in our image file or in this object, but we have to have in an external data frame. So we read that in using pandas, and then we have our labels again. For nice plotting functionality later, in images, we also extract the respecting coordinates of these labels. And then we can just plot it again. As we can see, luckily, there's a comparable structure going on here. And if we now not want to have a correlation matrix as we see here, but want to look how these things are represented in the brain, we can basically use our correlation matrix and the cohorts we find from before. That is the centers of these labels, these spheres. We can use the plot connectome function, providing our correlation matrix, the corresponding coordinates in MRI space, and plot it within like a classic last brain view, you know, from other packages as well. We can define edge thresholds and like different plotting things as well. As you can see, there's a lot going on. It's a very full graph. Every node is connected with every other node almost, and this is because what we also capture here are indirect connections. From starting Nilearn 0.5, we also have an amazing opportunity for interactive visualizations, where you can interactively explore your computed connectome. And you can change different things, just as the opacity of the view. You can reset the view to different angles. And this is a really nice feature to maybe include on a website or just explore to get a further idea or a better idea of how your things look like. And again, you have a lot of functionality to change the plot here. Going on to the next phase, leaving function connectomes, and we talk about seed to voxel correlation. So how one seed region is functionally correlated with every other voxel in the brain. Could be for resting state, but this could also be for task. You could think in the direction of like a PPI analysis. What we use here is, let's say you have a certain coordinates or region based on previous literature or like a univariate analysis. You can define these cohorts, set a sphere radius around these cohorts, and then use a different input method yet again called the Nifty spheres master, and from that extract the time series again. Here you can now specify even the time of repetition and a high pass and low pass filter, because this is of course important for functional connectivity data. As before, we apply it to our files and confounds, and to be able to compute a correlation to all other brain voxels, we simply use Nifty masker again and apply that like our brain master, where we basically extract the signal from every voxel inside the cerebral cortex. And then we have two time series, one from every voxel in the brain and one from our sphere or seed region we are interested in. And then to simply compute the correlation analysis, we just use we compute the dot product of our entire brain voxel time series and our seed time series, and then divide it by the length of our time series in order to have them standardized to a norm unit. Now, check these things out on the brain again. We just use the masker we defined for all voxels in the brain and can compute the inverse. So we can basically bring correlations back to the 3D image by taking the inverse transformation of the brain masker from our seed to voxel based correlations. And then it's basically any 3D image or statistical image you might know from like univariate analysis or something comparable. So we can use Nilearn plotting functionality to visualize that and even add a marker to indicate the seed region we used. And then you can do that for every participant or different conditions, and then you can compare these maps to see maybe if there's some sort of difference. We could also go from seed to voxel to seed correlation. So basically compute a correlation between different seed regions. As before, we define our sphere centers, our radius, apply it to our images. So you can see this is all like, it's always the same logic. And once you grasp that, you're good to go. Then we can check this out, how our spheres act, or like how the normalized signal looks throughout our different scans. And then for a change now, not compute the correlation matrix, but compute the partial correlation matrix, we just define a different kind in our connectivity measure, but then as before, apply it again to our time series. We can plot it as our 2D correlation matrix as before, but also display it as in our 3D image in our glass brain again, and in our 3D interactive surface here. Another route you could pursue with this kind of data is ICA and canonical ICA, where canonical ICAs are multi-subject ICAs. And the idea is basically you can extract brain networks in a data-driven way. So you provide your data and set up these ICA objects from the Nilearn decomposition module to extract regions that cluster together over time based on their signal. So you can set these things up with a certain number of components, set a certain threshold, is moving per between subject comparisons, and basically other things you know from the Nilearn input functionality or Nipype Nilearn functionality in a whole. And then, as before, you apply it to your files. Now it's not applying it to one particular file from the first subject, but to all files, because we want to extract regions based on all of our data on brain networks. And you can basically, like after fitting, you can rederive the computed components through the fitted object. And then you can plot those as a probabilistic atlas. As before the MSDL atlas, this is also now a probabilistic atlas because we extracted it based on our time series. We can also go through, so this plots all the regions we extracted, and we can also go through every single component and just work with one of those and go further. That's up to you and the analysis you have planned for that. We can even go one step further and do dictionary learning, where it goes in the direction of an ICA and comparable decomposition methods, but we have now we include sparse spatial loadings. So we basically incorporate spatial information into our maps, which usually gets you a better result in terms of spatial overlaps and shared signal and comparable things. As you can see here, this is defined as before using the CAN ICA object. We fit it, we can retrieve our images and then plot them again. As a whole, as a probabilistic atlas, I'll go through them. And then we included some comparisons between ICA and dictionary learning. Once you have that, you can also compute the correlation between the extracted components using the region extractor functions, fit it to your data, extract it, compute, set up a connectivity measure as before, and compute it again. So now what we have here is the function connectivity matrix based on our computed regions and our computed atlas. And then again, we can plot it as before, as you can see here. So in total, it's really all about these three steps, right? So you somewhat, depending on your analysis, you would extract your time series from different regions or from voxels. Then you set up a correlation measure depending on what you want to do there as well. It could be correlation, could be partial correlation, could be tangent space. And then you compute the correlation between the extracted time series, basically. And then you have your function connector. And for these other things, you also have the opportunity to compute different decomposition methods. For example, to compare between different populations before and after a certain training to investigate plasticity. So once you have that, you basically have the opportunity to compare and do a lot of analysis. And as said before, this is just a brief overview, basically. If I'm going to check the questions now, is there anything that is not addressed?
There are still a few questions open that are intended to address.
Do you want to, or should I?
No, I think I will address them directly in Slido, then it's also written down.
Okay,
the question
awesome.
was perhaps about the input data. Does it always need to be in Nifty? And the confounds always be in CSV file. You know it actually better. I can't remember if Nilearn, Nibabel gives a very easy way to transform from bricks and headers or from image and headers from SPM or AFNI into the Nifty space.
So, so as you can see here, like a lot of these things, the input methods, they work with Nifty. They are literally called Nifty something masker. So that's the easiest way, an option to get them out, and the same for the confounds. But it's not to say that you can have other input data and you can make things work. However, I think if you go from, so I haven't used these tools in a while though, but I think if you come from SPM and have like a preprocessed SPM file, you should have all the data in these files to like make these things work. And if you come from other things like AFNI or so, chances are you have to use Nibabel to convert images to Nifty or to a format that Nilearn can understand. But I've never done it myself. Okay, if you're addressing the other things in the chat, in the interest of time, we're going to continue. And now we're going to take the second thing here, which is we're going to use function connectivity and reutilize the data and the things we've learned in the function connectivity notebook to do some sort of more, let's say, realistic application. That is, we want to use function connectivity to predict age using machine learning approaches. So if you just click on this link here, depending on your setup, it might take a while. Here we go. And as I said before, this notebook guides you through a somewhat realistic example of how you would perform a machine learning analysis using function connectivity data. So basically, it shows you how to extract features from your data and how to use those features in a machine learning pipeline to extract certain outcomes and labels, in this case, age. And as before, we are a bit behind time, but I still want to say like 30 minutes, and then we're going to go through it again. And yeah, as before, if you have any questions, just put them in Slido and we will try our best to answer them and help you. So once more, I think the time is over. And as I said before with the other notebook, if you did not manage to go through all of it, don't worry, it's a lot. And you have the materials ready for you to rerun in the container. So while giving people maybe a minute to find the right window and get readjusted to me talking, a thing I forgot to mention at the beginning, we liberally included this notebook, but it was actually made from Elizabeth Dupree, Jake Vogel, and Guy Alvaro for a Nilearn tutorial. It is also on the Docs website, but we decided to include it here because it's really an amazing notebook and outlining fantastically all the different steps you might, or actually most of the time you need to undertake to do some sort of machine learning analysis based on neuroimaging data. We are, of course, aware that we are doing rather big jumps here, going from how to actually use Python to just open some neuroimaging data and work with that to performing complex analysis pipelines using machine learning in this notebook. Again, please don't expect from yourself that you will understand all of these things while going through it once. It's basically meant to be a showcase for this is how it's possible, and this is everything you can do, and there's even more, and these are important things you need to keep in mind when running such an analysis. Because another intention of this notebook and tutorial is to show you that comparably it's easy to do machine learning in some sort of sense with neuroimaging data, depending on the input and analysis you might want to do, but it's also very prone to errors and mistakes. Comparable to analysis pipelines, you have a lot of analysis choices and options that will up a very broad, versatile, long avenue of things where you could introduce systematic changes and problems and errors. And this also includes, of course, statistical pitfalls. So here we, and the original authors of Notebook to try to showcase this to you, that there's a lot of things you need to think about and that you need to motivate based on your data and your question, that you can just not run in a machine learning analysis easily as shown here, but you need to keep a lot of things in mind and test them. So basically the idea is, when we talk about machine learning using neuroimaging data, one option is, or one very common approach is that you work on the data directly to investigate something. So for example, this could be a searchlight analysis or an MRI decoding approach, which we'll talk about tomorrow. So for example, what regions of the brain are reflecting certain information. Here we're going to use machine learning and a lot of other approaches as well to make sense or predict something, some sort of measurement, some sort of outcome, some kind of demographic variable from neuroimaging data. In this particular example, we use resting state fMRI networks to predict the age of participants. However, this could also be, let's say, ICA components to predict a certain disease onset or progression. It could be some sort of anatomical feature to predict plasticity effects or different groups. So there's a lot of things, and you might get the idea of where this links to. What all of these things have in common is that you usually have a sample by feature matrix, where samples are your participants in this case, and the features are whatever you might want to use as a feature to something. And what you want to predict are labels. So for us, it's our participants with their corresponding age. And as features, we have our connections between brain regions and the resting state fMRI network. And the basic steps we need to perform. So in the beginning, it's just a bit of data wrangling, handling. So we get our participants. We have 155, which is a lot more than usual MRI analysis have. But in this upcoming age of big data, it's also not a lot. So if you work with HTTP data, ADNI, ABCD, PyBIDS, those have thousands. And if you go to the UK Biobank, you have more, way more. I don't remember the current number, but I think it's in the 40,000 range of participants that you can work with. So these are the numbers you need for solid analysis here. The basic pipeline for these things is that you need to extract features, then to evaluate or set up your model, and then to investigate your model. When it comes to extracting features, what we're going to use here is our resting state fMRI. We define some brain regions, we compute the connectivity, and then we apply a supervised learning approach. So as before, these are the things you already know from the previous tutorial. We get an atlas. We want to extract our time series of voxel time series from our resting state functional images. We apply it. We have our time series. And as before, we have our confounds and include them as well. We get a correlation matrix. And then we do that. So as before, this was just done for one participant. And then we just use a loop to apply this operation to all participants. So from every participant, we gonna extract the time series, we fit a correlation measure, and then we put this resulting correlation measure or correlation matrix into a list. And we do that for all 155 people. Depending on your machine you're running this on and the amount of resources your container instance has, this might take a while. For me, it took I think 2 minutes, but I'm also running it on a kind of fast machine. It's not good, but you could also just load it with this function here if you don't want to compute it for everyone. And what we have now in this, so this is our features now, right? So this is our connectivity matrix by participant information that we have. And therefore we have 105 participants by 2016 features. That is our correlation metric. And in our case, our feature metrics now looks like this. So now what we need, we have this part here. We still need our labels because it's a supervised learning approach. That is, we want to predict something. That is, we have a certain range of labels, a certain expression of a variable that we want to evaluate in terms of, can we use our features to predict this pattern or variable or what have you. There's also, of course, unsupervised learning, where you would not have these labels and provide that for your classifier, but you would just use your sample by feature metrics, use an unsupervised learning approach to let the classifier itself decide how many classes there might be. And this obviously depends on the question you have and try to answer with this sort of analysis. For us, again, it's supervised learning. So we have our sample feature metrics, and then we still need our Y, our target. That is what we want to predict. And what we want to do again is age. So we load our pandas data frame that includes demographic information for all of our participants, including the age group, was a child or an adult, gender, handedness, and some classic psychological measurements here. We grab age, and in most cases, that is in all cases, it's a good idea to check the data first. And I think I'm pretty sure, Bray, I've also looked at the material from the last workshop. Edwin did an amazing job at explaining how to analyze data and how to approach these things, not just blindly assuming that all of the things you have planned work on your data, but you need to actually check your data before running any sort of analysis. And this machine learning is no exception to that, right? So we're interested in age, and therefore it might be a good idea to see what we have here. So, and what we see is it's not, as most data in neuroimaging research, even though it's not neuroimaging data itself here, it's not a normal distributed data, right? So it's like a skewed here with more in the lower age group than the higher. And while we could just leave it like that, it might actually be a good idea to incorporate this information into our analysis. So when we get our training and validation and testing samples, so I think that's familiar concept to most of you. In machine learning, you have a train set and a test set, hopefully also a validation set, depends on the analysis you run and the question you want to ask and answer. So you split the data into different partitions. On one, you train your classifier, and on the other, you want to apply it to see how well, in quotation marks, it learned something from your data. Now that when we want to predict age and see that our age variable is not distributed in a way where we can just run our analysis and don't think first, we have to apply an operation called stratification, because we want to have in both the train and test set roughly the same distribution of the age groups, right? Because if you just would split it into train and test, and this age group could be that you're just training your classifier on the lower age group and then apply it to the older or vice versa, or some sort of non-equally distributed information. And this would, of course, heavily bias your outcome. So we stratify our analysis by age, meaning that in a train and test set, we have the same amount, roughly as good as possible, given our data, the different age groups and expressions here. And then we can run our first model. We use a support vector regression because it's a continuous variable, right? It's age. It's not a yes or no thing. It's not groups. You could do groups and define age as groups, but with this sort of distribution of the data, a regression might not be the worst idea. And we can just basically fit it. And also here again, we provide you with some links where you can look further into different classifiers and models and what's out there. If you use scikit-learn and Nilearn and other Python libraries are really good in bringing neuroimaging data or any kind of data that you want to analyze with that into a format that scikit-learn and these machine learning libraries can understand well. And we basically get our classification running. We can see amazing, almost a perfect fit. This is why everyone is doing machine learning and we're all good to go. This is clearly our Nature paper. However, you know that is not the case, because in machine learning, there's a lot of things we have to think about and we have to assess and incorporate into our analysis. And this is basically what the other part of the notebook and the tutorial is showing you, right? So you're going to be sure that your train and test set are distributed accordingly. Then you're not overtrain and overfit on one and the other. Be sure to analyze certain quantities, certain characteristics of your model. For example, the accuracy R squared or the mean error. And then we go further into different aspects. That is what kind of cross-validation you can do. The k-fold, leave one out. And other things, how you're going to tweak your model. And I'm not going into detail here because, first of all, time. And second of all, it's going to get very, very detailed. But if you have time and are interested in these kind of analysis, I highly recommend this tutorial and the notebooks and other tutorials and resources that are linked throughout it, because it gives you a very nice idea on all of these different things and how they run. That is including feature selection, feature transformation, how you can tweak your hyperparameters, how you can assess them, the influence on the results that you're getting out of that, different models. You can see it's getting very, very into detail here. And the last part also deals with how to assess, for example, feature importance. That is, if you have a range of features, which we have here, because we have a whole brain functional connectome, resting state connectivity matrix, we might be interested in, are there certain regions and connections that more or less drive the classification? That is, are some features more important than others, right? Because chances are these are also not very equally distributed. It could be that from 100 features we use, only maybe 10 are very informative and the others are not, and therefore introduce noise into our model. So with these kind of things and the steps here, we also show how you can access those. And then also, of course, because we're still interested in neuroimaging and the brain, we can use Nilearn again to bring it into a format which you can plot and assess accordingly. So we have our feature importance here as a correlation matrix, 2D. We can put it into brain, into 3D space. We can threshold them because of the collections, and we can also use our 3D interactive plot to visualize important connections. That is, connections that are important for our classification task at hand. Okay, again, I know it's a lot, and it's definitely, if you have not worked with either of these things, definitely an overkill, but please be aware that it's totally new normal to be overwhelmed. And if you want to check it out later, you have the materials, you can look through it again, check other tutorials also in Nilearn docs, and this will definitely help you starting with these things. So are there any questions for this part? Michael, I assume you monitor the
so there are no questions. No.
Okay. Okay, cool. Then we continue, and so just an update on the time, because we said we would finish now and start open discussion. So what we do is we go to the slides, and then I will cut those to 15 minutes and just do the rest tomorrow. And after 15 minutes, we're going to start open discussions. But I'm also happily answering questions while like during the presentation. That's no problem. So I'm gonna start. Okay, Michael, is it working? With regard to
yes.
Okay, nice. Okay, and this I said before during the introduction, this slideshow is basically intended to capture the essence of these workshops we're doing here. That is, provide you with pointers and things that are out there so that you are aware of them and can start using them if you're interested in. And here we basically gathered and assembled all the things. We unfortunately don't have time to go into detail in today workshop. So just as a disclaimer, the things we're going to present here are, of course, only a subset of everything that is out there. And they are, of course, heavily biased towards our experience and knowledge, and are by no means complete. But we just include the things here we have experience with and we can talk about and provide you with further information. But it's much more out there. And if you have suggestions, additions, and feedback for these things and things that should be included or presented differently, please let us know so we can further improve our materials. The main focus here really is the core aspects of the community-driven development that is happening in the neuroimaging, Python, open, reproducible science community. It's all about open, reproducible neuroscience. It's about sanitization, how to manage your data. It's about fair neuroscience, how we all as a community can get together, engaging in the support of these tools and other people. And of course, it's also about inclusive neuroscience. That is making these tools available and usable to as many people as possible, independent of their background. And it's really important to think about the entire research flow. What we put here is the so-called rainbow of open science practices that provide you with pointers for tools that you can use throughout your entire research workflow and life cycle of a scientific project, and how to make it more open, reproducible, accessible. And within this presentation, we're going to do that tailored to neuroimaging. And our roadmap would basically, we'd first talk about data standardization. And of course, we're going to talk about PyBIDS in this case. Then we're going over to so-called PyBIDS applications, going further into Python packages and other amazing things that are out there that are not directly PyBIDS apps or Python packages, but things that build up on top of them or just integrate them or something completely. And today we're basically going to talk about PyBIDS and PyBIDS app and leave the rest for tomorrow. So I would say that, or I would assume that a lot of you already heard about PyBIDS, if not all of you. But just to give a brief summary of the idea of PyBIDS, the question is really how you manage your data within your lab, within the institute and beyond. How you store them, how you structure them, is there any metadata on it? Do you apply version control to your data? Because usually every researcher has their own way of doing these things. This might even vary across projects within the same researcher. So the problem with heterogeneity in data management is that it's very hard for others and you to understand your data and keep track of changes along the process. So you have unnecessary metadata input, the codes and scripts have to be adapted, and it's just a huge effort to automate workflows. And there's no way to automatically validate data sets and results. And sharing these things for reanalysis is just basically impossible in that sense. So therefore, a while back, PyBIDS was introduced as a directory structure based on common practices. And it builds on existing standards, such as Nifty, JSON, and TSV files. And it's intended to be legible for humans and machines to automate as much as possible. You also have the PyBIDS validator for checking compliance. And you have a lot of information online where you have the basic PyBIDS landing page, providing you with general information, how to get involved, how things are working. And then you have the specification that you can check where all these different aspects are outlined in further detail, also for different modalities. And you can go through all of them if you have questions and want to see how it looks like. So regarding metadata, the basic metadata here are in the file names that you have subject, session, the imaging modality, different tasks if you have task-based fMRI. And these are usually enough to generate unique names for your data that makes it easier to know what's going on there. For example, here, if you look there, we have subject 1 has anatomical images, functional images, and diffusion-weighted images and these modalities are also indicated in the file name. For functional images, we also have the different task indicated here, which is just a resting state scan, and we have that for all of the participants, right? Additionally, Nifty headers and JSON sidecar files, they contain detailed image reader metadata that you can also query review if you have any questions, but also to automate certain processes. And you still also have the dataset description, .json, participants.tsv, sessions.tsv, and scans.tsv, which do record study level metadata that may not be associated with specific file names by the dataset as a whole. There are different ways how to get your data into PyBIDS, and most likely you're in one of three main scenarios. You have data already converted and no access to the DICOMs. You have the data already converted and access to the DICOMs, and you have data still on DICOM. Where scenario 1 is clearly suboptimal, there are still converters for this situation. So if you have your data converted to something than DICOMs and want to apply PyBIDS or bring it into PyBIDS, there are more and more tools out there that allow that. However, of course, it's easier and more straightforward if you have the DICOMs ready and just convert it directly from DICOM to PyBIDS as indicated here. And for that, you have a bunch of different tools out there, and it's getting more and more basically by the month now. For example, you have built-in tools in software analysis packages such as AFNI. You have very common famous DICOM to Nifty converters, such as DICOM to Nifty X. They have PyBIDS functionality in them. And you have dedicated tools like UDConf or Repronym that integrate these tools and do the conversion in a very automated way for you. For example, Repronym is a very great example of that, where already at the scanner in your sequences have certain specifications and names. Therefore, also the DICOMs you get out of them, and then you basically apply the converter or UDConf, integrating it with DataLad to apply version control to your data, and what you get out of that automatically from the scanner is your data conform to PyBIDS and under version control. So you don't have to do anything by yourself. But of course, this heavily depends on how things are running at your center and how these conversion processes are typically handled. There's also the PyBIDS validator out there where you can just go, you can either use a Docker image for that or an NPM package, but it's also a web version where you can just go to and indicate a folder or a PyBIDS dataset. I'm just going to do that here. So I have my example dataset in PyBIDS here. I click upload. Please be aware, it says upload, but nothing will be uploaded. It just checks file names and folder structure and nothing else. No files will be uploaded to the web. And if I do that here, unfortunately, I have a lot of problems. It already tells me that my dataset is not PyBIDS valid, but I can see all the different information I have in my dataset. I have one subject, one session, the available task, and the available modalities. And then I can go in this information here to check what are the problems and how can I solve them. So you don't have to go through each and every subject by yourself and see are there any problems or are there any deviations, what have you. It's also is not only for neuroimaging in the sense of MRI. Since a few years already, right after it got introduced, it started to expand and being updated to different modalities. And this is all really happening through community-driven development. So this is not some sort of, I would go organization or what have you. It's really the people that are in the field are driving these standardization efforts and get together, which is, I think, just amazing to see. And these days, if you have already been incorporated into the main PyBIDS versions, that is, for example, EEG and MEG, and a lot of other extensions are currently in the making, such as eye tracking, PET, SWI. I think genetic also got merged recently. So there's a lot of things. And if you have the feeling that something is missing there and you could be helpful or be interested, just go to the website, and everything is organized at first in Google Docs, and then it will be transferred to GitHub. And people are very, very eager to help you within this process. So please, if you want to be a part of it. So if everything is machine readable and we have a certain data structure we can expect from PyBIDS confirmed data set, it's actually super easy to automate processing pipelines and workflows. And this is done in a thing called PyBIDS apps, PyBIDS applications. So these all share a set of core command line arguments, and they should not depend on software outside the main container. So within, you have a dedicated container for a dedicated pipeline and workflow. They are all hosted on Docker and Singularity Hub, have different version tags, and they're really meant to target automated and standardized analysis that are reproducible. So you pack your pipeline and workflow into a container, which is your PyBIDS app. You integrate continuous integration testing. You put it on Docker Hub or Singularity Hub. You can use an HPC, and then you can run the same pipeline wherever you want. And to reiterate that, the problem really is that there are a lot of sources of analysis and results variability, as introduced briefly in the Conda and Docker section, where PyBIDS apps aim to address these aspects via a common interface, the container technologies, and standardization. You see those like different aspects coming together here, and we can apply open analysis on open data. And there are more and more available PyBIDS apps out there. If you go to the website and check the apps, you can see there's basically for everything you might be interested in terms of like a rather classic or common processing pipeline, it's there. So you have free server, you have SPM, different Nipype pipelines, diffusion images, so it's all there. And we're just going to talk about a few very useful and common PyBIDS apps that are out there, starting with MRI QC, which is quality control for structural and functional images. So all you need, again, is your PyBIDS data set. You download the Docker image using this command here, and then you can just run it on your data. And it will provide you with an extensive and comprehensive quality control, computing a versatile range of image quality metrics, and you even get intuitive output reports and summary statistics for your data. It even includes a pre-trained classifier to predict pass or fail for anatomical images. So if you want to do quality control, which hopefully you want to, MRI QC is definitely the way to go. Talking about structure analysis, there's a very cool PyBIDS app called MindBoggle, which computes a lot of structural features that are central to a lot of research questions. It's focusing on shape features that are volume and surface based, and provides you with intuitive summary statistics such as mean, standard deviation, supports volume and surface data, has different output spaces and regressors. It's very nice. You can have standard things like thickness, surface area, but also more sophisticated is the wrong word, but like more detailed and advanced approaches, just as travel depth and geodesic depth measures or Laplace-Beltrami spectra. So MindBoggle is really a nice tool for that. Of course, the I guess most famous example is fMRI prep, and it addresses the variation problems related to pre-processing and structural and functional imaging data. It processes an extensive comprehensive pipeline for both of them, and you have a lot of different specifications in terms of your workflow. So what you want to do in terms of realignment, output normalization spaces, and what have you. It is very easy to apply. It provides you with intuitive output reports and summary statistics, and supports, again, volume and surface data, also output spaces, and different regressors. So for example, the confounds we introduced or incorporated in the previous examples, they all come from fMRI prep. And you got all of these things automatically by fMRI prep. Talking about function connectivity analysis and related things, if you are into these kind of analysis, you know there are a lot of options of how you could denoise your data. And this choice is not obvious in most cases. There are some things, some rule of thumbs people agree on. Having the same denoising strategy for different data sets is not a given. So what fMRI denoise does, it builds upon BIDS and fMRI prep and comparable outputs. And it's a pipeline for strategy comparison of different denoising strategies, and can also apply denoising to your data. And it's basically act as a function connectivity quality control. And as the other BIDS apps, it provides intuitive output reports and summaries you can work with. So remaining in pre-processing, going a bit away from the things we already know. There are also now BIDS apps for diffusion-weighted imaging, such as QSI prep. It's basically, you could say, like an fMRI prep, but for diffusion-weighted imaging. I think there's also MRI prep, but we decided to include this one here. And it actually goes a step further. So not only has it a pre-processing steps usually or originally applied to diffusion-weighted imaging, but also steps upon it, like built upon that. That is a reconstruction, a connectivity estimation, and all of that in there. Again, just to have your BIDS data set ready, download the container, run it on your data, and you even get quality controls and confounds, output reports, summary statistics, all in an automated way. CPAC is basically also it's comparable to that, but focuses on resting state fMRI data. So it's dedicated pre-processing and analysis pipeline for that. And one of the newer things, it's called FitLins, where you can apply, or it's targeting linear models, building upon BIDS derivative, for example, from fMRI prep, and the BIDS stats model specification, running automated linear models first, or individual level and group level analysis on your BIDS derivatives data. Again, as usual, it's old news by now. You would have quality control metrics and confounds, for example, correlation of regressors, and you get intuitive output reports and summary statistics for all of them. Just as a bonus round here, all of these things, or a lot of these things, are now organized in Nipypes, where they basically come from the same people that did MRI-QC, fMRI prep, and FitLins, but now it's getting a bit more versatile and spread. So things are getting more disentangled into their own dedicated components, where you have the same software infrastructures as Nipype, Nibabel, BIDS, and PyBIDS. Then utilities that are somewhere within there. This is Nip workflows, TemplFlows, Nip transforms, and then you have applications that integrate all of these things, such as fMRI prep. SMRI prep is also a thing that's coming, and MRI-QC just is represented. And with that, I'm done. And tomorrow we're going to continue there with the Python section and the other amazing things we want to show you. I think now we are open for questions and discussions, right? So discussions, questions now, at least when it comes to me, could be to any of the things we talked about. It's no problem.
I think there's directly. Sorry, yeah, continue.
Yeah, no. It's all good.
There was a good question regarding BIDS. Do I need to install each BIDS app plus the actual toolbox in Python, or how does it work?
No, that's a cool thing. You don't need anything but the BIDS app, because the BIDS app it's a BIDS app and it's working like that. It has all the Python functionality and workflows in there. So for example, let's take fMRI prep. The basic underlying architecture is a Nipype workflow. So it includes Nipype and this workflow and all these things that you need in order to run the application. And that's what really comes in. Think about it as an app, like on your phone. It has all the components that it needs to run and conduct the analysis or workflow that it does.
And perhaps the crucial part, you've mentioned it before, to run the app, you need Docker. And that was also, well, or not? There's not a Docker free version.
I mean, could be Singularity.
Well, yeah, Singularity, or you could also set it up on your system, but the easiest is Docker or Singularity.
Yeah, I think a lot of the PyBIDS apps actually have like what we call bare metal installation. So it's like a Python module you could use. But in that case, it is assumed that everything else, the underlying software packages and what have you, are available on your system. So if you want to use, let's say, MRI QC as a Python package and want to run it on your analysis, you need all these underlying tools on your machine available and set up in a way that the workflow can use it. When possible, definitely stick with the PyBIDS app in the container version. It's easier, more straightforward.
Cool. So yeah, we're ready for all questions. If you have some, if you just want to discuss something during the day, or yeah.
We're of course also open to like your experience. If you maybe not, maybe convinced is the wrong word, but if you have had a bad experience, or if you think these tools could be changed, or just anything, just let us know. We got a question: not be able to install Docker. I'm very sorry. Okay. That's the case for you. You're not alone with that. I think Docker can be a hassle depending on what you're running it on. And the question is, will it be useful to participate in tomorrow's workshop? I would. I mean, we're obviously biased, and of course we say yes. I think that depends on what you want to do. So you can definitely follow the examples. On Michael did set up the MyBinder version of the workshop. So you can definitely also do the workshops and the tutorials interactively using MyBinder. So you don't have to install anything. You just need internet, and that's okay. And it's good to go. And then you can go through that. And for the rest, I guess it depends. If you want to learn about these different tools that are out there, check them out. And if you want to apply them. So I don't think having Docker right now running on your system is a necessity to check out the other things Michael and I are going to talk about tomorrow.
No, I think there might be a few processes that might crash, unfortunately, because of memory requirements. But most of it should work, or at least the exploration should work. But we're also happy if you contact us. We're happy to check in with you directly how to set up Docker. Perhaps there are two other questions. So how much of what just covered, so the bits part, etc., is available via MATLAB or for MATLAB analysis?
Very good. And quite often recurring question. That's fair. One got to say that the majority of the things we show you and we present here in terms of tools are focusing on Python or maybe Bash or like Shell and other things. MATLAB is, I think, less supported just because the people that are actively like in the community engaging and supporting these things, developing these things, they don't use MATLAB. And of course, it's also harder to include a software that is not open, right? So it's possible to include MATLAB in a container. For example, if you don't want to include MATLAB but something comparable, you could just use Octave. I think it's called, right? Octave. So that's possible. You can put it in the container. I think, I'm not sure, Michael, please correct me if I'm wrong, or anyone else. It should be possible to include MATLAB in a container, given that you can provide a license to it and run it. I'm not sure.
There's also a way to compile MATLAB code to create standalone applications, and those can be run without a license. So if if you're using a specific MATLAB application, some of them are developed that way. So for instance, you can use SPM in that way. So you can run SPM inside a container without needing
Exactly. Yes. Thanks, John, for adding that. For example, the Nipype parts Michael's going to show tomorrow will use SPM, I guess, in some way. And also the examples we showed you include SPM, but as Johan mentioned, they include the so-called standalone version of SPM. And this uses the MATLAB compiler runtime to compile a set of MATLAB functions, and whatever you have there, into a standalone application. So you can run them without running MATLAB or having a MATLAB license. All you need is the MATLAB compile runtime, which you can download or the execution thing there, and the compiled software. So definitely SPM has that. I think CAT 12, whatever is pronounced, has that. The structural pipeline they have, so you can use that for sure. And when it comes to other MATLAB things, there's currently like a group that meets a lot. I think Remy Gao is one of the persons that is heavily involved in there, and they actually try to bring more of these things to MATLAB, to not have that much focus on Python. So there are definitely things happening, and if you want to help out there, I think it should be enough if you Google like BIDS MATLAB extension support community, you should be able to find that. And when it comes to software, as far as I can remember, SPM introduced a BIDS read function in one of the previous releases. You can actually like have a tag or like a menu item, a button where you can say read from BIDS dataset or read BIDS dataset, and then automatically, because it's machine readable structure, right, can access the dataset. And for any like add-on analysis, I think it doesn't really matter, right? If you want to do machine learning with MATLAB instead of Python, or like use other toolboxes there, the images can be used within that. I think like one thing you need to be aware of is that SPM, I think, cannot read zipped image files. So you would need to unzip. You would need to unzip the data, but then you can use it because it's just a 40 nifty image.
Mm-hmm.
I hope that was helpful.
Yeah. I think so. Yeah. So perhaps also to go to a question that was in the Zoom chat. So the question was to explain a bit more how to access files that you have on your machine to make them available within Docker. So let me actually, for this purpose, quickly share my screen. So here you should see my screen, and now if I just open quickly a terminal here. So the command that I've shown that we can use was the Docker run it --rm, and then well, it had also the port to decide how to access these files, how to access the web browser. And what was missing, what I left out because of time, was an additional command which allows you to get stuff that is inside the Docker. So I now add just a quick command which is saying bash. So instead of running the Jupyter notebook, I just want to have run the bash, get access to the terminal within the Docker image. So if I do that, here I see the notebooks, I see the program the program notebook, I see the slides, I can see all the content of all the notebooks and so forth. So I just entered the Docker as with a terminal and not as the Jupyter notebook version, to highlight this question about the files going back and forth. So now, for example, if I have here a folder called output, a folder called output. So this is a folder at the very top structure. If I create a new file called new file, that is empty. And if I want to get this one out, I have no possibility to get out of the Docker environment. Because when I started it, when I opened it, I didn't give any possibility to access these kind of. And to do that, so let's create a new folder quickly on the desktop. So I call it my data, something like that. And what you can do is in the Docker command, you can say, you can give it this as a V tag, so volume tag. And here I would say structure of my machine. So if I say my user on the desktop, and then the my data. So this is the location to my data folder. This is the location to this folder. And I can say I want this location to be available under the folder /output within the notebook and within the Docker image. So with this -v command, I can say that this local folder should be represented in this folder within the Docker image. And if I do that the same way, I can open here already just to highlight what will happen. I can go back to this output folder, it is empty again because I closed the Docker container, so everything was removed. And so if I create my notes once more, it directly writes it into this output folder, which is connected with my folder on the desktop. And so this is the approach of how you would do it. And so going a step further, let's say you would want to run fMRI prep. So you would there you don't need these tags, but you could do something in the direction of I forgot again if it's PolDrac Lab or just PolDrac. You would say it's fMRI prep. You can then say only do it and here I'm not sure in more single subject 15 or something like that. And then you can say that on your desktop in your bits folder, so that would be the location of the bits folder, and then you need to specify that this is actually the input folder and these kind of things. And so the exact specification on how this should be done is in the bits app explained which folders you need to provide. But what you would do is you would provide a number of folders of input and output folders. You would say the bits app that you want to run, you would give it some instructions and then press enter and everything happens.
Yeah, just an example, I actually pulled up the fMRI prep docs. So we're going to do a switch in terms of who shares screen. And as Michael said, usually these things are very well outlined in the documentation of the things you're interested in running in. So what you can see here now is the fMRI prep read the docs page. And here you got an example for how to run it using Docker. So you would have Docker run -it, -srm, old news by now, but then you have like all of these different volume mappings, right? And as Michael said, you have one that does mount to data. And as we talked about briefly, it is actually indicated as read-only. So this is your input data path. And their data can only be read but never change, which is a good idea because you will only want to have like derivatives somewhere else, but not like change your actual raw data. And then you indicate one folder for derivatives and where the output of the processing pipeline should be stored. And then you got one for the working directory, so where intermediate files will be stored. Again, you specify what you want to run. Now it's actually called Nipype because this development is happening. And then we call fMRI prep, indicate the data input, output, and like other things you might want to specify the workflow with. So this is how it's done. And in the same way, instead of mapping a directory, you can also directly mount a file if you need like a certain license file or what have you.
And so there was also a question about on Slido, would you use MRI QC and fMRI prep in the same analysis and in which order?
So in the same analysis pipeline, okay, so you would definitely, I would use both. Let me say it like that. I would definitely use both. And I would use MRI QC before I would use fMRI prep. MRI QC is very, very handy in showing you and providing you with insights about the quality of your data. So for structural images and functional images, you have like background noise, the amount of the motion, signal deviations, all of it in there. So doing that as a first step before you run any pre-processing and other analysis is a good idea, just to get a basic sense of your data set's quality and if there are any major problems. Because of course, like some things, like a folding, or if participants moved a lot, those who would also see at later stages, hopefully, if you check your data. But MRI QC is very good in also unraveling things that are not very easy to detect. Or also, I think it's the case that a lot of people that do neuroimaging are not trained to perform quality control, which is fair. But things like MRI QC can definitely help you there because they provide you with the outputs that are necessary to easily grasp what's going on and to see if there's a problem. So I would use MRI QC first, evaluate my data based on that to see if like some participants are off, if everyone is off, could also be the case. And then maybe based on that, decide if I already want to exclude some participants because they moved a lot or there were other problems with the sequence or what have you. And then after that, apply and run fMRI prep and follow-up analysis.
I agree. I think that's all questions. We're happy to answer more or otherwise. close the session for today.
Oh, thank all of you for being a part and asking interesting questions.
I want to give you a 5-10 minutes quick version of what Nipype is, how it works. And so some of you might have already seen this logo or this page. Let me actually link to the real page. So this one is the Nipype page with this nice logo. It has all the information. It has explanation what it is, some examples, some guides, but the better way to digest and to get used to it is probably the Nipype tutorial, if I can only get to it, that I've written a few years back. And so we will see this one also a bit later, how you can teach yourself really in-depth knowledge. So this morning we will talk about the basic concepts, but there's also more examples, workflow examples, and so forth. But coming back to the slides, Nipype is an open source developed software package. It is, I've checked, currently we have 193 contributors, 193 people who worked on this code, who participated, who added, who to make this package very versatile and smooth working package. There's a huge community in the background, as just mentioned, and it's all written in Python. And the reason for Nipype, the name Nipype, Ni for neuroimaging, Py for Python, and PE for pipeline. So the main goal was to streamline any kind of analysis that you could do with a neuroimaging toolbox. So if you take SPM, FSL, Freezer, AFNI, ANS, and all of the other ones, some of them work well in MATLAB on Windows, some of them work only on Linux machines, some of them need different specifics. And so the goal of Nipype was to create a common interface in Python so that it is easy to learn the language, how to use it, and have this common interface allowing you to switch between packages. So you can do and we will see that in just a bit, you can do the motion correction with SPM, you can switch to the co-registration with FSL, you can do some surface projection with Freezer, and so forth. And so Nipype is not a new neuroimaging toolbox that will replace the others. It will give you the skills to integrate everything into one streamline. And so as such, it is very flexible and it can create very complex workflows, which we will see also in just a bit. And so to just briefly recap, to hopefully introduce it from your background, if you use SPM or some other toolboxes. SPM is a great tool. It's also how I started to learn about neuroimaging analysis. But there's often a lot of clicking. There's MATLAB license involved. So using Nipype, you can something like here, the realignment, which is highlighted as the first step. If you want to do that in Nipype, you can, or the smoothing, sorry, you can do it rather straightforward. You say from the Nipype package, I want the SPM interface. So Nipype interface is SPM. I want to have the smoothing object. And so you declare it, you say, okay, I want this smoothing object specified as this variable name. I have a few inputs. The input is in files. The input files is this functional.nii. So this will be your functional nifty file. You specify a smoothing kernel and you can run this node. And that is how quick a Nipype interface can be used. So using the smoothing function from SPM. So in the background, actually SPM is run. In the background, a MATLAB batch is generated and executed. But for you, in your Python code, you just need this code snippet. And so coming from the other side, from FSL, FSL has also a great GUI, which allows a lot. You can also learn how to use it in scripts, which is also very powerful. In my experience, it took me some time, but once I understood it, it replaced for me SPM, as it was very strong and very capable and flexible as well. But also in this regard, you might have, again, a lot of clicking. You don't know about some default parameters that you would love to know more about. And so using Nipype, again, gives you the liberty, the flexibility to do to use FSL tools. So here we do the same thing as before. from nipype.interfaces.fsl this time. We import the MC flirt, so motion correction with flirt. We declare the object. We define the input, so where should what is the input file to be used in the motion correction, and we run it. And one thing that is very powerful with Nipype is in this regard here, for example, this there's a command line in the background that is executed, and you can access this command line. So it can give you directly the bash script or the bash command of how you could execute the MC flirt in a separated command if you're curious about. And so this is also a great way to explore the different things FSL can do by setting it up in an Nipype framework and then look at the different changes in the command line. And so you might also say, well, I don't use FSL much, I don't use SPM, I'm really a surface guy, so FreeSurfer is my tool of choice. But also in this regard, Nipype can help a lot. So if you ever did the execution of recon all, or also want to do some other steps that might need to be done in parallel, or where certain steps can be done in parallel, Nipype has a great strength in this regard. So let's say you have the two hemisphere, you want to project, or you have the data project on the surface, you want to smooth it on left and right hemisphere, for example, on 6 subjects at once, and as each of these steps is independent of each other, you could do that in parallel. And so Nipype gives this flexibility to do many of these steps in parallel. So the code to do that would look something like that. We would do, again, from Nipype interfaces, the FreeSurfer interface, import the surface smooth. So this is the smoothing function for on the surface. You declare the object. You say the input file is something like that, where you have a placeholder here. And then you can say that actually this node should be iterated over the term hemi, once for the left hemisphere and once for the right hemisphere. It should, sorry, I apologize. It should once be smoothed with a smoothing kernel of 4, once with 8, and it should be done with these 6 subjects. And so here, this iterables explodes that to 2 times 2 times 6. So 24 different parallel processes. And then you can, slightly different than written here, but you can run this node in parallel, and everything that can be done in parallel, if your machine allows it, can be done directly in parallel. And that comes also back to SPM pre-processing. If you have 20 subjects, if you don't open 20 different MATLABs to have 20 different runs, you're stuck with a serial execution. And so Nipype gives this flexibility of doing everything in parallel if possible. And so tying it once back together, with Nipype, you can use your toolbox of choice. You can stay 100% on SPM, you can stay 100% on FSL, but you can also combine them and combine the flows and profit from the strength of each of these packages. And yeah, it gives you all the advantages of each package, while it allows you to control the disadvantages of the other packages. And so if we look at a very short example of how this can be done, if we now think about, we have our raw data set, that would be a data folder or something like that. We have 3 subjects, 1, 2, 3. And now just to make it as versatile as possible, so this is not necessarily a good processing pipeline, but let's say you want to do the motion correction with SPM, then you want to switch to the co-registration with FreeSurfer because you did the segmentation and parcellation of your anatomy. You want to normalize the data with advanced normalization tools, or ANTs. And then you want to do the smoothing with FSL because you're in favor of this smoothing, for example. And so here we switch from SPM to FreeSurfer to ANTs to FSL, and we have 3 different subjects. And the way how you would implement that in Nipype looks something like this. Again, first you would specify all of these packages. So we have interfaces from FreeSurfer, the co-registration. We have an interface from ANTs, which is the normalization. In FSL, for example, we would use the Susan smoothing workflow. In SPM, we would take the realign for the motion correction. And so you import all of these interfaces. Then you need to create each of them, as we did before. And what you can do is you can directly already specify some parameters that you want to use. So the motion correction, we can register to mean, we can set that directly to true. And for example, in the smoothing, we can directly specify the smoothing kernel we want to use. So here, 6 millimeter. And so once we have these nodes, after we imported the interfaces, we can tie them all together. Well, that actually comes in a second. The other part that is also here highlighted is that we need to get the data from somewhere. So we need to have an additional node that tells us the data is coming from this input folder. And we need to specify where we want to save the output in. And so this can be done, for example, with these two functions. So data grabber is one of them, and the data sync would be the other one. Data grabber, as its name says, you would specify where the data is stored at. So what is the base directory? And then you have some information of how to get the different subjects, so subject 1, 2, 3, which runs you want to execute, and so forth. And once everything is executed, you can put all of that in a data sync where you would define of where should the output be stored at. And also here you can define an output folder. And so everything what's happening, everything that's happened, so you get the data from somewhere. In between, there's a lot of intermediate temporary files. And at the very end, you specify exactly the files you want to save in this data sync folder. And if you want, after execution, you can remove the temporary files and you only stay with exactly the outputs that you want to generate. And so that is a huge saver of disk space. But we will see that also in a second a bit. And so once we have the nodes, we've created the different motion correction, co-registration, the smoothing nodes, and so forth. We need to create a workflow object. And so this one is an object on which we want to attach all of these nodes. And so in this case, let's create a workflow node that is called pre-processing flow, so pre-proc flow. And the only thing that we then are left to do is to connect these nodes. And so this syntax here is not exactly the syntax that you would use. We will see the right syntax in a second. But what you would say is take the data from the grabber node, so from the input node, take it and give it to the motion correction node. The motion correction will run, and once it's finished, it will move it to the co-registration. Once the co-registration is done, it moves it to the normalization, to the MRI template, for example. After that, it goes to the smoothing node. The smoothing node smooths the functional data, and then you store these smoothed functional data in MRI space to the data sync. And so this is a specification of how you want to decide the data flow through your workflow. And once everything is set up, you can just run it with the .run command. You can specify that it should be done in parallel or in series, in linear fashion, and then it's executed. And so to recap everything, Nipype is really an interface. It doesn't replace any of your other tools. It's an interface that is hopefully easy to learn, that can quickly be understood thanks to it being in Python. It allows you to create these complex and flexible execution workflows that you can also transmit or send to other people, that you could also package in a Docker file and so forth. And you can execute that with many different ways. So you can do the parallel version. You can really run it linearly on your machine. You can push it to a cluster server and have 300 subjects all being executed at once. And so in this regard, it's a very versatile, flexible toolbox that allows you to profit from everything that is out there. And so the key parts are really the individual nodes that can be packaged into a workflow, but also the workflow itself. So here we have one of the nodes is a workflow itself that has a lot of nodes in it. So you can have this encapsulated structure of these workflows. And yeah, that is the end of the slides. What I wanted to do next is to showcase how this can be done in an actual example. And so in this regard, I've run this Nipype showcase. So that's the one just directly here. I've run this on MyBinder. So this one works on MyBinder. Later stages are having some issues, but we come back to that. So coming back to a simple example, let's say, and I make it a bit bigger, let's say you have a very straightforward, simple pre-processing analysis pipeline for functional MRI images, where you just want to do slice time correction, motion correction, and then smoothing. And so as mentioned before, what needs to be done is we need to first import the building blocks. So that would be nodes and workflows. And then we can specify which interfaces we want to use. So in this case, for a first run, we will use everything in FSL. So we use the slice timer function from FSL. We use the motion correction from FSL. We use the smoothing function from FSL. And so we import that so that we can use it. And then we create these 3 nodes. And so here, there's a small nuance. So we create this node. So the slice timer node, we say the index directory is actually meaning if it's ascending or descending, if it's interleaved recording of the slices in the volume, and what the repetition time is, the TR. So I can directly specify these kind of parameters, and I will show in just a bit how you can know which parameters can be used. But so here I specify the parameters to execute the slice timer node, but to use it in a workflow, I need to also package it inside of a node, and I need to give it a name so that we better understand which name does what. So here I could also just say slice time or just slice or something like that. If this is informative enough, that is good enough. And so this is how we would create the slice timer node, currently stored under this variable. The motion correction node, where I specify, yes, it should be aligned to the mean. And the save plots just means I want to create these typical FSL motion correction plots. I want to save them as well. I package it once more into a node, and then this node is also ready to be used later on. And the last one is the smoothing node, as mentioned before. Here, let's say with a smoothing kernel 4. And so doing all of that, we now have our building blocks, each of them packaged into a node. So the next step, what we need to do is we need to get a workflow. And here I say I want a workflow which we currently store in this variable. And for this particular example, we will not use data sync or data grabber. We will just directly say everything that's happening in this workflow, actually store all of the temporary files in the current location that we're at. And so we have the nodes ready, we have the workflow ready. The only thing that is still missing now is creating the workflow to connect everything. And so here we say, this is our workflow. So we have our workflow. We want to connect some parts. And there are 2-3 different ways of how you can write these connections. I think the easiest to read and to write are what we see here. So we say that we have the slice timer node doing the slice time correction and the motion correction. We want to connect this one to this one. And what we want to do is we want to have the slice time corrected file. So these are the output files from this node. We want to connect them to the in file of this motion correction node. And in the same way, once the motion correction is executed, we want to take the out file of this motion correction node, and we want to feed it into the in file of this smoothing node. And again, we will come back to what these names are, where they come from. But so this is now creating the structure. It's connecting these nodes to each other. And so if we use this write graph function, we can rather quickly, if we visualize it, then here see what's happening. So we have a slice timer node, which uses the FSL interface. The output, the slice time corrected files as an output will be put in as input into the motion correction node, which is FSL. And this output here is then fed into the smoothing node, which is an FSL interface, and it will be fed into the in-file field of this node. And so now running this example to see how it actually works, what we are missing, what I mentioned before, is the input file. So in this case, we don't use data grabber. We just directly say, yes, input file for here for the slice time correction. So we specify directly the input of this slice timer here. The in file is this functional image. This is one particular functional image of one subject. And we say, let's take this input file and run the slice timer node on that. And then the rest will pass through the whole node, whole workflow. And so the last part that is also crucial that I've mentioned before is when we run the workflow, we can say that it should be run on multiple processors on your machine at once. And we can also specify how many processors or threads it should use. And this, of course, if you don't have if you only have 4 threads, 2 CPUs, you cannot run 200 parallel processes at once because it will crash. But you can play around with this number, and perhaps depending on your data set and your the power of your computer, you know how much you can use so that it stays stable. And so in this regard here, we run now this one subject through the whole pipeline. Let me already start it. In parallel, if possible. Now I have an error message, of course. I haven't executed it, sorry, my mistake. I had to also execute this cell. So if I run it now, it runs the whole thing in parallel. It's difficult to get used to this output, to read it, but it says always here, it gives some more log file information. And for example, here it said currently running. So here we can see that the slice timer node was running for some bit. We see that my current machine has about 8 GB of RAM. I specified to have 5 processors, and currently it's using 1. That's why 4 are still free. And then it says here the slice time correction was finished. It is completed. And so it moved in here onto the motion correction. It used here the motion correction is run. It also gives us an information of what is exactly the code that is run. So this one is the whole code, the whole motion correction node with the alignment to the mean, with creating the plots and so forth. So everything that is actually executed is hidden here in the log file. We see once more that currently it's running in the motion correction. We need to wait a bit. But yeah, with this log, you can see how the data is moving through it, where it is stuck, where it's currently at. And in theory, it should take about 2 minutes to do these steps. So 2 minutes to do the slice timing, then move it on to the motion correction, then moving it on to the smoothing part. And again, this one uses as much FSL as a pure FSL script would use. So it runs here the motion correction. It runs here the slice timer correction. So you have the exact FSL command, and it runs the exact FSL routines. And yeah, let's wait. So it finished with the motion correction. It switches now here to smoothing. It runs the smoothing. Here again, we have the smoothing command. That also helps now to understand these different parameters that FSL might use in the background. The smoothing is running here, but it's very quick, of course. And so everything is done in about 2 minutes and 4 seconds. And so it took now 2 minutes and 4 seconds to execute the slice timer, the motion correction, and the smoothing. And so if we look at the outputs that were created in the working directory, so these are the temporary files. We have here the graphs that we looked at before. So these are the images where you see how the data goes through. And of each of these folders, so for the motion correction or the slice time correction first, we have a file with the command that was used. We have the slice time corrected file. We have the motion corrected file. So here slice time corrected, and motion corrected. And we have the smoothed file. So that's why it's here the postfix as well smoothed. So we have all of these 3 files there. And now the first part to showcase why Nipype is super powerful is, let's say we want to now change something in the smoothing kernel. So we don't want to smooth it with a smoothing kernel of 4 millimeters, but with 2. We can quickly change this parameter and run the process again. And as you can see, it says here slice timer was already executed. So it was caged. You can reuse the same output it had before. The same for the motion correction. And only the smoothing part was outdated, and it had to rerun it. So that's why it rerun it. It was currently running for a few seconds. And after 14 seconds, the whole pipeline was finished again. So just because we only moved the smoothing part in the pipeline, so only the last part, it didn't have to rerun the previous one, and very quickly it was finished. And in a similar way, you can also, we could have also specified that we wanted to smooth it with a smoothing kernel of 2, 4, and 8, and it would have done everything, the motion correction and the slice time correction in one step, and then doing the different smoothing kernels, split it up and do these 3 parallel processes in parallel. So it would have also been very quickly. And to showcase that, let's create a fake example where we just duplicate this initial workflow. So we create 4 additional clones from it. Let me directly run a few things and then I will explain what's happening. So I've cloned the initial workflow that took 2 minutes. I've created a bigger workflow, a new one that I call here the meta flow. And I added each of these 5 workflows as nodes into this meta flow. So if you visualize that now, we see here, let me try to make it a bit bigger. We see here, again, just this, and this node. This one is the same structure we had before. So the slice timer, FSL interface, the output goes into this input, goes to this input. But here we see also that it's now the workflow, the sub workflow or the pre-processing workflow, 1, 2, 3, and so forth. And as you see that all of these 5 things, because each of them, each of these workflows are independent of each other, they're on the same height, so which indicates that all of them can be done in parallel. And so that's also what's currently running in the background. So here I specified again, use 5 threads at once. And first of all, it said that the first, no wait, let me go here. It said that it runs now 5 different slice timer at once. Here it says it's still running 3 because 2 in the meanwhile already stopped running. If I go a bit further down here, it says 2 motion correction nodes are currently running. Here it updates again that now all the 5s are running. So you can see here with all the individual MC flirt motion correction for one pipeline, motion correction for another one. You can again from this log file read out what is happening. I will not yet show how a crash looks like and how we need to interpret, but yeah. And of course, the strength now is here that these 5 processing pipelines, they can be done in parallel if your machine is big enough. And so before we had 2 minutes for one pipeline, and now it should also take about 2 minutes for all 5 of them. And so this is especially if you have 20 subjects, if you have 40 subjects or 100 participants to analyze. If you can set it up in a parallel way, you might be even able to just run it overnight and you come back and your data is pre-processed. Or let's say more specifically, your whole data set, not just, I wait briefly here. But what I wanted to show you before we go to the next section is the strength of Nipype. So while this is running, and I actually cannot push it, I quickly will check if there's already some questions. If you have some question, don't hesitate as before to use the Slido framework. So yeah, one question was, how does Nipype deal with updates for interfaces? So if FSL updates or there's a bug fixer and so forth. Nipype adapts to it. It was, again, Nipype is heavily developed by 190, or well, there are at least 20, 30 core people who are updating these kind of things. So you on your side, you need to update FSL. You need to make sure that you have SPM 12, for example, instead of 8 or 5 or older versions. But the interface of Nipype, so coming back to the slides, for example, these kind of interface, that stays the same. If now in the background, some default parameters change, that's another question. But yeah. Does the Nipype, so there was another question, does Nipype require the data to be bits organized or organized in the bit structure? By no means. And also for in general, Nipype doesn't need Docker. Nipype doesn't need bits. Nipype doesn't need anything special. So if you have on your machine FSL installed, or if you have on your machine SPM with MATLAB installed, you can just install Nipype. You can just install a Python environment, ideally with Conda or Anaconda. But you can, yeah, you can run this directly in a script, directly in a terminal. You can run it through a notebook as we show here, but you don't need to any of these other specifications. Yeah, the bits framework we will see in the afternoon helps to streamline it because, yeah, I will come back to that in a second. So now we saw this whole analysis took, it didn't took just 2 minutes. My notebook is unfortunately not the strongest, but it took 3 minutes for 5 times the workload that we had before. And so this shows that instead of 10 minutes or waiting for 10 minutes in a linear fashion, we can really profit from this parallelization. and now checking again the output of this metaflow. Here we have the pre-processing as we saw before, all of the outputs, the second one, the third one, and so forth. And so to prevent all of these intermediate files that you might not need, you can now use data sync to only store these outputs. And sometimes you're happy to have these intermediate files, but what we will see a bit later is that if the whole thing in parallel can be run so quickly, and if you can change a few things of not aligning to the mean or changing the smoothing kernel, the rerunning of your complete data set might actually be quick enough so that you don't need to spam your hard drive with a lot of data. And so coming back to the strength that I've addressed earlier, here we use now all only nodes from FSL. And so now let's switch first, let's switch the smoothing node. So let's say that we want to use from Nipype interfaces, we want to use the realignment from SPM. So here, if I do realign, I have this realign node. And so again, what I would need to do, I would need to create this node, but I might not know what goes into this node. And so there's this nice help function that you can use to better understand what is the input, the output, how does this node work. And if I do that, we get very quickly the help page of the realign node. It says here it's an SPM, it's from SPM interface. It gives you a short introduction of how it could be used. So in a similar way that I showed in the example, the input file is this functional image registered to the mean and so forth. But it also gives you a much more detailed explanation of what is the input that you need to provide, so the mandatory input. So this is the input file, and here it says input files. So where before we had, well, I'll show that in just a second. So this one is the important keyword that we need to use, but we also have the job type. We can say, is it just an estimate? Is it just a write? So to SPM people, this should be familiar. Or is it estimate write? So estimating and the reslicing. Which smoothing kernel would you want to use in the realignment? No, in the smoothing, sorry. Register to mean, no, I'm in the realignment mode, yeah. The realignment to the mean if you want to, but this smoothing kernel, for example here, this is also accessible in the SPM GUI. So if you would click to the different options, you would find all of these parameters. So this gives also a nice transparency as to what else is possible. So the interpolation steps during the reslicing and so forth. So you see here all the possible inputs that you can give it. You can see all the outputs that come out of this node. So you have the mean image that you can further execute. You have the realigned files. So these are the files that were executed, were realigned and resliced. And you also have the realignment parameters. So these are the translation and rotation parameters. And so coming back to that, we know we have the output. It's the realigned files. And we know the input needs to be in_files. So if we check here, we keep that in mind. So I write quickly input in files. And this is just, this is not actual Python code. This is just a note for afterwards. So what we need to do is we imported the package. We can just copy paste what we had here. Now I actually switched the example, I realized. So this one is the realigned one. We want to register to the mean. So this we also had. Sorry, I quickly do the help point page again. So we have here the register to the mean. We say we want to register to the mean. We can do that. Register to the mean equals true. And we just for keeping it working in this example, I will also call it motion correction flirt as before, so that then the variable name is reused and I don't need to change that for now. Let's do, we've created the node. We now need to again execute this one, recreate the workflow. And here now we have again this node, but here the slice time, the in files is not in files, but it's now has this additional S. So this we need to be careful about. If we don't have this one, it will give us a quick feedback of motion correction doesn't have in files and motion correction doesn't have out file. So we need to address here in files and the output that we saw before that I've just deleted. Here is the realigned files. So here the output of the motion correction is this realigned. And now if I execute that once more, I have now recreated the workflow. I can visualize it again. I see now in this overview that I have the slice timer in FSL. I have the motion correction now in SPM and then back to FSL. I just realized there will be a crash, and I will highlight that in a second. So if we run it, the slice timer doesn't need to be rerun. Sorry. The slice timer doesn't need to be run. That's why it says cage, so everything is fine. And the next step created an error. And so these errors, reading this error is also a skill set that you will see in just the next section. But what can we see if you scroll completely to the bottom? You see above the error message, you see here a quick recap where it says that actually the motion correction crashed, and the crash node information is somewhere in here. What I know and what was addressed yesterday is that FSL's output are compressed NIfty file, and SPM cannot handle these compressed NIfty files. So some steps need a bit of tweaking, but this can be done rather quickly. We can say that the slice timer node should not give back compressed NIfty file, but actually normal NIfty file. So if I change here the output type of the slice timer to NIfty, I can rerun the whole thing. I can set up everything I had here, create the workflow once more, and then run it, and now everything is fine. So because I've changed a parameter in the slice timer, it needs to redo this part. It switched now to the motion correction, and this one is not the SPM. And so this is the setup of how you can switch a module. So to recap, we just had to import it. We created this node that's the part that changed, and we had to reconnect it with the new names of input and output, and potentially change some parameters so that it's not compressed. But all in all, it was changed, and now it goes through the motion correction, and once this one is finished, it continues and goes in the FSL smoothing and so forth. So yeah. So one of the questions on Slido was how would you find out how many pipelines your laptop can handle, or parallel processes? Usually it's rather straightforward. If your computer has 4 CPUs, it's capable to run. So it's a quad core. It's capable to run up to 8 parallel processes. So you can work with that depending on knowing how many CPUs you have or how many CPUs are available. That is one part. The other part is certainly the RAM. So if I run it now in this setup, I only run one subject. We see that this step only took like 200 megabytes of RAM, so I can easily scale it. But sometimes I see I might have a more computational intensive node that directly takes already 2 gigabytes of RAM, and then you can play with that. So usually the breaking point is the RAM, the amount of RAM. But yeah, if you have 16 gigabytes of RAM, you should be able to run about 8 processing pipelines in parallel if you don't do anything else. Or you do 6, and it still is much more efficient than just a serial execution. To give you once more the big picture of Nipype and PyBIDS and Docker and all of that, if we go, for example, to the fMRI prep, that I don't have open here, fMRI prep toolbox. So this one is a toolbox that Peer yesterday briefly introduced in the slides. Some of you unfortunately already had to leave because of the timing, so I will very briefly recap. fMRI prep is a toolbox that is brilliant. It does pre-processing of anatomical and functional data. It in this nice figure highlights and showcases what it's capable of doing. So it takes the anatomical T1 weighted images. It does inhomogeneity correction. It does some reorientating that it's in the same space as the MRI or the same direction as some templates you might have. It does skull stripping. It does recon all. So it runs everything. Also spatial normalization. So normalization to the MRI template. It does all of that in parallel if possible. But it also uses takes the functional images. Does also their brain extraction, meaning masking of the skull, motion correction, slice time correction, susceptibility distortion estimation. So if you have depending on your direction of your gradient, it corrects these kind of things as well. It registers your functional image to the anatomy, and so forth. So it really does a lot at once. And so what's happening here in the background are actually Nipype pipelines. So if you're on the fMRI prep page, and if you scroll just far enough down to the pipeline section, so where it indicates, let me see where I find it here, processing pipeline. So here we have a processing pipeline for the anatomical images or for the functional ones. If you click on it, you see that this is, again, it's a different way of writing a workflow. It's just giving the nodes without the input and output. But here it says which nodes are connected. This is another step where it also does the referencing of the bolt to the anatomical images. And so the fMRI prep uses many different pipelines, many different Nipype pipelines. And for example, here, it's a bit more complex one where you have different nodes. So input, different nodes, it goes into a sub workflow. And in this sub workflow, you have the red workflow, which in itself is again a sub workflow. And so everything that is on one line is in parallel. So here, these 3 steps can be done in parallel. Here, these 4 steps can be done in parallel. And it gives you nice information and also something that you can share in your papers of what is done. And so fMRI prep uses this Nipype framework, so this pure Python framework with having access to FSL, SPM, FreeSever, and all of the other tools, and package that into a Docker image. And that's how you're able to use fMRI prep in a pure Docker environment. So I'm not sure, there's somewhere here the Docker container instructions, how to use it as a Docker setup. And so what's happening is many of these toolboxes that are currently developed, so fMRI prep, diffusion prep or DTI prep, MRI QC for quality control, they are encapsulated in a Docker image, but inside they're using actually a complete Python Nipype framework. And so the nice thing is, if you're very curious to see what this susceptibility distortion functionality does, you can look into the code of fMRI prep, and you can take these functionality or even a workflow and put it into your own workflow. And so by such, you gain a lot of flexibility to better see what other people are using, better integrate other people's workflow into your own code. Yeah, and hopefully through that gain a lot of flexibility. Let me check once more if there are no questions. I don't see at the moment. So as a next step, I would propose that we, when we look at the program, so no worry that we are over time because I've introduced already a few concepts that you will also see in this section. So I have dedicated here about an hour of exploration of the Nipype building blocks. And so here, this part, if you click on the slides, you can see that it actually points you, so very quickly, introduction, it points you very quickly to the basic concepts that we saw before in the Nipype tutorial. And so this, I would say, is what you could do for, let's say, the next about 40 minutes. So let's say at 11, we come back. So if you open it, initially it doesn't look as nice because I had to find a workaround. So it has all of that, but the moment you execute it, so if you just run this cell, it renders it much nicely. And this one is now the interactive Nipype tutorial. Here you have the tutorial, here you have some introductions. So the showcase was what we just looked at. But what I would love you to do is to go through these basic concepts. So what is an interface, what is a node, what are workflow, how to visualize them, and just look at as much as you can, go through them. Don't worry, it's a lot, so certainly not can be covered within an hour. But yeah, for the next 40 minutes, 35 minutes, go through them, and then we will come back at 11 and I will recap some of these steps. And of course, if you have any questions in the meanwhile, don't hesitate to use Slido, and I will be active in answering questions there. So see you in 35 minutes. So I think as it is 11 o'clock, I think we can continue with the next section. So first, I wanted to quickly recap what you have seen in this basic concepts part of the Nipype tutorial. So let me once more share my screen. So there are many different things that we highlight here. The interfaces themselves, what are interfaces I've shown already in the showcase a bit, how they need to be connected to the nodes, how these nodes need to be in workflows. In this part, it's explained them in a bit more detail. We have then also ways of informing how you can create your own interface, how you can have from your own MATLAB library or something that is not yet integrated in Nipype, how you put this one into an interface and make it available in nodes and in workflows. Some section of how to create the different kinds of visualizations. So having these bubble graphs or going in a more colored version here, or going into this detailed version where it says exactly which outputs go to which input location. And so all of these tools, you don't need to know them in detail to use Nipype, but they allow you much flexibility. As mentioned before, the data grabber as a one input way to get the input in your data is certainly recommended. But others like the BIDS, the PyBIDS setup, Pierre will show that in the afternoon in more detail, will help a lot to integrate if you have a BIDS data set, or if you get a BIDS data set from somewhere, from somebody, you can just have a standard BIDS, PyBIDS setup, and your workflow runs on any BIDS data set. And so this is a huge strength in this regard, but Pierre will cover that more in the afternoon. Different ways of storing the output to making sure that only the files that you want to have saved, to save them in a specific way. Different Nipype plugins. So here there was the text about linear execution of multi-proc execution of running it on a cluster and so forth. One thing that I think is very strong and that I use more and more often are these function interface. So here there's just a short example of how you could create your own Python function and then package this add to function inside a node. So here that we would say which function you want to use inside this node. And this one is very strong and very powerful because you can, connecting it to yesterday, you can have here a function that uses some Nilearn routines that plots this glass brain, or that does some ICA, or that does some any kind of other manipulation. And so you can say here that this one would be a nifty image that comes in. You have some Nilearn resample image. Then you would say what your T1 be, what is your input image, and then you return something like this resampled image. You just return it, and that is more or less how you can very quickly create a function, feed it in here. You need to then adapt these input names. So that would need to be this input, and that would need to be this output. But like this, you can have create your own function, your own. You could run here your own Bash script, your own Python script, your own MATLAB script if you have MATLAB available. Put it in a function and just put this one node into your have it a smooth transition through all of that. This I will mention in a different way here. So if we go to the recap, if we go back to the slides, I've summarized some of the key points. So with the .help, you can better understand to what the node or what the interface requires. You need to package it into a node if you want to use it in a workflow. If you just want to use it as a standalone thing, you can just use this kind of setup where you just would use that directly. You put it in a node to then connect it in a workflow. This is how you create the workflow. This is how you connect nodes. So with the output of the first one, connecting it with the input of the second one. You can write the graph to better understand how the data flows through your graph and what the graph looks like. Again, you have many different input and output versions of how you can get the data and output the data. Different ways of executing it linearly, in parallel, locally, in parallel on a server. How to use this function to create, to handle data from your pipeline and transform it and feed it back into the pipeline. Iterables, also very strong. And so this is something that we see, for example, down here. So let's say you have A would be, let's say, a motion correction node, and B would be a smoothing node, so where you want to smooth your data. But now you would say, as mentioned before, you want to have a smoothing kernel of, let's say, 4, 8, and 16. So by just adding this iterables command to this node and saying on which parameter it should iterate on, it will split the pipeline into 3 analog or simultaneous paths. So each of them is then doing exactly the same thing, and you don't need to specify that it's actually afterwards 3. The iterables command will take care of that, and then everything here from here on can run in parallel. But there's a lot of other functionality, like the map node, which allows you to do some processing, and then let's say you have, let's say you would, for some reason that doesn't make sense, you make anatomical segmentation, then you get gray matter, white matter, and CSF files, and each of these 3 the masks you want to smooth or to resample, you can quickly say run map node, resample all of these 3 in parallel, and then give all of the 3 as one list back into the C folder in the C node. So here is a way to split quickly this function and to put it back. So while iterables just duplicates the following sequence, this one allows you to just do one sequence in parallel and then back in. You have many more functionalities like join node, synchronize, and so forth, to handle other characteristics of a workflow that you might be interested in. Before we go to the next section, I quickly wanted to just show what can be done if this is pushed to the brim. Somebody took the recon all pipelines from free server to reconstruct the anatomical or the surface reconstruction, and deconstructed all the individual parts into Nipype pipeline. And so here we would have a typical first section. I assume it takes a second. The auto recon, the first part, with all these individual nodes and sequence of stuff that can and cannot happen in parallel. And so it would do the first part of recon all, the second part of recon all, some of them in parallel, the third part of recon all, bringing it all together and saving it into 1-2 final folders. This one is not necessarily how I would recommend to do it, because the recon all pipeline from free server is very well optimized. So you're gaining a bit of time, but not necessarily much. But it's just a showcase of how you can create really big and huge analysis pipelines. For example, you could combine everything. So all your pre-processing, first level analysis, second level analysis, and then creating output. You can combine everything in a pipeline and then have it packaged, sent to a friend, and if it's just in a Python framework, package it in a Docker image if you want to use it for other data sets. For example, if you have them in BIDS data set, you can really very versatile just apply it to other data sets. And so being mindful of the time, if we go back to our overview, now the last about 50 minutes are here to create your own pipeline from A to C. And so just to give a short introduction, the goal here is to have a pre-processing pipeline that does a few different steps. This is by no means the best way to do it. This is by no means just a copy-paste that you should use for your other projects. I've written it in such a way that it highlights many different things, that it points to some new things. For example, the artifact detection is a nice tool that is also available through Nipype. But I just wanted with this one to highlight how versatile Nipype can be, how you can switch between FSL, SPM, and some Nipype-specific toolboxes to go through motion correction, slice time correction, motion correction, artifact detection, anatomical segmentation, co-registration, smoothing, applying this the mask, the brain mask to a functional image, and then also to even linear detrends, so taking general trends in your data out, and then be finished with this data set, pre-processed with this data set. And so for the next 40 minutes, so let's say till 10 to 12, I would recommend, I would suggest that you go through this pipeline, There are, of course, exercises in there. I have some of them. If you want to do it, certainly nice experience. If you want to rather read through it so that you get about through everything in 40 minutes, that is also fine. And again, don't hesitate to ask questions on Slido. I will answer them in the meantime and answer them in the big chat right now. And so I saw one question is, can you import other MATLAB toolboxes? So not if they're SPM specific. Yes, that is no problem. There's on the Nipype tutorial, there's, if I can find it here, there's under advanced concepts, SPM with MATLAB, I will need to quickly check it, but I can link into the chat. But it is possible to integrate other interfaces. You just need to spend a bit of time to making them available. To either you create your own interface, or you use what I've shown before, this function interface, where you just have a node that runs MATLAB code, and once this MATLAB code is finished, it comes back to the pipe. But yeah, so let's be back at 10 to 12, and then we can have the last summary and question round. So as it is 10 to 12, I will now come back to the hands-on of the pre-processing pipeline and just summarize a bit that, and then also highlight a few questions that were mentioned in Slido. So let me share the screen once more. So here, just as a quick recap, you hopefully were able to go through most of it. As mentioned, we have here a rather complex pipeline that shows different functionalities. And so as before, let me change the resolution. As before, as a first part, what we need to do, we need to import these building blocks, so the node and the workflow. And here, this is also an example where you can see how Nipype, for example, could be used outside of the framework of a Docker image. So if your institute doesn't allow Docker and you only have MATLAB available on your machine or somewhere on the server, you can also, with this kind of command, indicate where Nipype will be able to find the SPM. And so this one is a pointer of where this particular SPM 12 version can be found. And so the main frameworks are set up. Then, as before, we create a workflow on which we want to attach everything. And so for this example, in this notebook, what I've decided to do is step by step, I create a node and I try to connect it already to everything I can. And so starting with the first one, we had to unzip our files because they were coming as compressed Nifty files. So we used this GNU gunzip for the decompression of the Nifty file. We specify the input, we specify what node it is or what type of interface we want to use in this node. We package it into a variable name that we can use, that we later will connect to other things. And now, particular to this data set is, for example, that we have non-steady state recording at the beginning of the scan session. And if we just, for example, look at one specific voxel, we see that the signal drops very quickly to something and then is kind of on the normal track. So what we could do in this regard is we could decide to cut ourselves these first 5 volumes out. And so this could be done with FSL extract ROI function, where you could say on the time axis, extract the first or remove the first 4 volumes, save them as an uncompressed Nifty and give them further. There are also other interfaces already available that can automatically detect the number of non-steady state volumes and would be able to remove them also with no problem. But so here, after compression, decompression of the file, we just cut off the first 4 volumes. We connect them, so the unzipping, we connect it with the extract ROI one. So we have the out file from the unzipping, the in file from the extracting. We then give it further to the slice time correction node. And in this case, we now implemented a version of SPM, which is called slice timing. Slice timing is a slightly different setup as the one we used before that was FSL based. So we need to indicate the reference volume. We need to indicate how many slices we have, the TA, the TR, the slice order, and in this case, the slice order would be just this list. And once this is ready and packaged once more into a node, we can make it ready and connect it to the output of the previous point where we cut off the first 4 volume. And so the whole thing is repeating itself and again and again. So the motion correction from FSL, again, registering to the mean, we connect that to the output of the slice time correction. We can use something like the artifact detection, which we'll see in a bit, which can be used to detect if a participant moved a lot in the scanner due to motion parameters, translation, rotation, due to sudden signal changes. And so there are many different parameters that you can use here. You would then connect the relevant inputs. So the artifact detection node needs the realigned files, so the functional files, plus the motion parameters, rotation and translation. So you would connect them. Here we would use the segmentation from SPM. It's not too relevant how this is written. This is very specific to the way SPM does it with the tissue probability map. But we would say that we want to have gray matter, white matter, and CSF, for example, or here also the head and then other regions. And so again, we create the node, we say what the tissues are that we want to extract here, and we connect that to another node. And again, as before, because this new segment is an SPM node, we first need to decompress the Nifty, that it was in compressed version. So we create another node that unzips the anatomical image. We connect these two together. We then have also the issue of coregistration between the anatomical and functional image. There we could use the flirt command from FSL. We can decide how many degrees of freedoms we want to use, which cost optimization function, and so forth. So there's a lot of detail that needs to perhaps be once researched or to be seen from this tutorial or other examples. But once they're set, you usually can stay with them. And once you have this pipeline created, there's no reason of dynamically adjusting that for every data set. So once this works, it should work very smooth for any of your data sets. Again, connecting everything for the coregistration, where you would need the mean image from the motion correction, the output, the unzipped anatomical image. For example, for some other steps, you would need to threshold your binary mask. So this is from the segmentation. You would want to threshold, you would want to take the white matter mask, the probability mask from 0 to 1. You want to threshold it at 0.5. So everything above 50% probability should be considered a white matter. And as an additional argument, you can say after this threshold, binarize the whole thing. So everything above 50% should become a 1. Everything below should become a 0. And so you could use this node to quickly transform these kind of data to then, from the segmentation, give as input this threshold. And there's a small nuances here as well, an additional one. Usually what we saw before was a setup where we had the output of one file. So we had the segment has this output and the threshold has this input. But what's actually happening, the second segment, as we know, has 6 different segment files. And so what you can put in between is you can say that the output of this one, we put it in the brackets themselves. This output is a list of files, and this list of files should go through this function, which is just this small function where we say extract the first volume, or actually the second one, which is the white matter. So 0 here would be gray matter, 1 would be white matter. So you are able, so to speak, on the edges of your pipeline to quickly insert a function that handles the text output that is coming from these different nodes. And so connecting everything again, I will speed up a bit because of time. We put that all together. We transform the mask into the right space. We apply a smoothing. We create all of that. We make sure that all of the inputs are there for the different nodes. If we miss one of them, and one of them was a mandatory command, we will get an error that will tell us you forgot to provide this relevant input. So you can work around with that by just implementing it. And so once everything is done, a very quick look at this data input version. So here we don't use the data grabber, but we use the select files. So as we've seen before, the data is, in this example, stored into this folder here. So we have many subjects, so subject 1, and this subject 1 has subfolder which are session test. So you can access this test. And so this is the bit structure that we talked about in previous many times, so anatomical and functional images. And so if the structure is always the same, you can once set up a template. So this subject 1, this 01 will be replaced by this parameter. This test that we have here will be replaced by that. And this one is the second subject 1 that is coming from here. So you can create a template that knows what is the subject ID, what is the session ID, what is the task. So if it's now a detection task or something like that. And then you can specify that during the iteration here. You can specify how it should be filled up. So the session ID, so this part should be filled up with a test to represent what we have here, and so forth. So once your bit structure is clear, you can either specify yourself how this works or use PyBIDS, which we will see in the afternoon. Connect all of that, give these select files to the right compression, decompression nodes, run the notebook. So if we visualize it, we see actually we did a lot of different steps. So all of that here can be done in parallel to this over here. This one is the huge FSL Susan smoothing flow workflow. Everything is at the end detrended. That might be a nice pointer as well to nonetheless highlight. So there's a function that Nipype provides, which is under the confounds interfaces. So it's a Nipype internal function, which is called TSNR, so temporal signal to noise ratio correction. And here in this function, you have the possibility to say that it should remove polynomial of first, second, third, fourth degree, which would could just remove trends for a polynomial of 1 or U-shaped things and so forth. So this one is a nice way to remove some basic trends. So it shouldn't replace the high-pass filter that you want to use perhaps in other instances, but it is a way of getting some already a few detrending mechanisms in there. And so once it is run, it will create a lot of outputs. So each of these nodes will create different outputs. And because of this reason, because of these many outputs, we recommend to perhaps use a data sync to get it quickly all together. And so what is nice on these Jupyter notebooks, again, is that you can combine visualizations and quickly explore how did it work. So here, if we explore the rotation and the translation parameters of this one subject, we see that it seems to go in the right direction. We can plot the artifact detection. And so here, this is the general image intensity changes. So if somebody moves a lot, supposedly the intensity from frame to frame should also change a lot. So a pixel that was bright suddenly becomes dark. And so that is what this upper part is looking for, or the lower part of how much a subject moved in space. And here I on purpose set the threshold rather low. So normally you would have this one at 1 or 2 millimeters, or perhaps the size of your voxels. But this artifact detection can then quickly identify that these volumes might be create an issue, so that you might want to mask them or handle them in your preferred way. And so using these Jupyter notebooks, using Nilearn, using all of these functionalities that we also saw yesterday, you can quickly visualize how well did the gray matter segmentation, white matter segmentation, CSF, how well did they work? How does your brain mask look like? How does your mean image look like before or after motion correction, after it was co-registrated to the anatomy? You could overlay it here on the anatomy, how it looks after smoothing. And so it gives you a quick way to also do your own quality control to make sure that everything is well done. So here, masked mean image, here we masked the functional image with with only the gray matter. So we made sure that we only kept functional voxels in the functional image that were actually on top of the gray matter voxel. And so, yeah, there's a short section about how to then save it in the right way to only keep the relevant files, so that at the end, what you get as an output would be only, for example, that, where you have the artifact detection information, you would have the motion parameters, visualize the motion parameters from the motion correction plus the very final functional images. And so instead of having all of the other intermediate files, you could set up your Nipype workflow to only keep these few files. And then again, here's an example. I've run it on 2 additional subjects to just show that it can run smoothly in parallel and without any change. So just by specifying that you actually have a few more subjects to execute, everything runs in parallel and finishes once it is finished. I will also, sorry already for already be 5 minutes overdue. Yeah, I actually will. I pick up these questions that were mentioned. I could pick them up after lunch. So don't hesitate if you have some other questions. But I will pick them up in the afternoon lesson at 1 o'clock. So bon appetit to everybody, and see you at 1 o'clock again. So welcome back, everybody. I think we will wait just another 5 minutes till everybody is back from lunch. But good morning, Pierre.
Yeah, once more, good morning from the beautiful city of Montreal, and happy afternoon, early afternoon to all of you folks over the pond. How's it going?
Good.
Nice. How was the morning? Getting all Nipype and stuff.
I hope informative and interesting to everybody. It still stays a strange thing to give a workshop for 40 people without seeing and hearing anybody, but
that's true.
Questions are coming in, so I hope it is
that's
interesting,
good.
Stimulating. So yeah, perhaps this afternoon, Pierre will lead us through different things. One thing is, again, how to use BIDS, PyBIDS, how to do statistical analysis with fMRI images, but we also have a bit more machine learning, multivariate pattern analysis, and some awesome new tools that he will introduce in his innovation slides. Perhaps something I can show while people are joining was something that we were asked yesterday after 3:30. I will share my screen quickly. So if you, for example, if you want to run Docker, and again, we will briefly recap why Docker is useful or why it is not necessary. But if you run something like the Docker command for this workshop, so let's say I run something in this direction. I quickly need to update something here. But so if I run the command, sorry, this one is the command that we're actually using. The question is how, once you're in this notebook, once you're in this Docker environment, how can you access file on your machine? And so one possibility to do so is to use this -v flag. And so I very quickly want to touch on something. So if I enter the Docker container just with bash, so I don't create all of this Jupyter notebook, I'm right now in the location where the program is stored at. Or I can also go to the output folder. And so in this output folder, this one is currently empty. And so if I create a file called notes, a markdown file, this is just in this output folder, but I cannot access it. But if I, for example, now create a folder on my desktop, my outputs, and if I now use the Docker command once more, but with this -v for volume flag, if I use it and link directly, if I link directly to the desktop and link to this my output folder, I can map this output folder to the output inside Docker. So right now I say that this folder on my local machine can be used inside at this location. And so if I do the same step as before, if I then have this mapping ready, I can again go to this output folder, so the one that was specified here. I can create a file, and now it's directly also on my desktop. So this is just to give a very quick showcase of how Docker can be used with this V flag, with this mapping, how to use it to get data inside your container and outside of your container. And I think as it is almost 5 past, I will also already start to answer a few questions that we had in the morning session. I can stop with the screen sharing. The questions were, again, a bit Docker related, Nipype related, SPM related. So one of them was how, for example, can you use other SPM plugins with Nipype or with the runtime compiled version of SPM. And so if it's already runtime compiled, you cannot use these other plugins. If you have access to SPM in your MATLAB, you can create interfaces for these plugins in your Nipype code. But more importantly, Nipype is, again, completely standalone. So you don't need to have SPM. You don't need to use the runtime compiled SPM version. You can link to SPM version on a server somewhere. You can link to your local FSL installation, to an AFNI installation somewhere else. Nipype really gives you the opportunity to use the framework, the packages wherever they are, the interfaces. Yeah, this is with respect to SPM and Nipype. With respect to Docker, the question was also what kind of alternatives to Docker exist. What else can you do if Docker is not possible on your in your institute? And so again, once more, the Docker thing that we're using here is a great tool for the workshop to quickly communicate or provide you an environment with SPM, with FSL, with data already prepackaged. But it's not needed for anything we show in your in this workshop. You could also install everything locally yourself on the system, and you wouldn't need to use Docker. But Docker is a great tool for things like fMRI prep, MRI QC, all of these other tools that Peer already touched a bit upon. They can highly profit from Docker. But if you're not interested in Docker, if you don't want to use Docker and you can run everything locally, then you are perfectly happy with Anaconda or Miniconda, setting up the Python framework and then just interacting with these other packages. And I think another question was also, and Peer can take over this one. The question was, can you do everything in Python? Why do we need Nipype? Why do we need FSL, AFNI, SPM, and so forth?
Yeah, just like a quick add-on to the question before, also already here on the Slido deck, the person mentioned that they are working on a Windows work PC where they can't use Docker, obviously, because it's, I guess, managed by an overarching IT department. And as Michael said, with most cases, though, you can, if it's all about Python, right, you can do that with Anaconda. That's okay. And you also don't need escalated privileges for that. You don't need to be root to use these things. You can just install it for a given user on your machine. However, if you want to use other tools, let's say FreeServer, FSL, and what have you, those just don't run natively on Windows. And you also can't get them with pure Anaconda-based things because it's beyond pure Python, right? So in these cases, what these software packages usually offer is a dedicated virtual machine or a Docker image. If you can use Docker, therefore, the virtual image, the virtual machine might be an option, a way to go for you. That is, you can have a virtual machine dedicated for FreeServer, for FSL, AFNI. You can have maybe a bigger one with everything in there. However, as mentioned in the Anaconda and Docker session, those things can get very big, very fast. Then if your desktop machine, whatever you have there, is not very powerful to begin with, a lot of resources will be dedicated to the virtual machine. Therefore, everything will be running rather slowly. However, depending on how you set up your workflow and what you do, it's possible. It just might take longer. Back in the day, I did some analysis on Raspberry Pis. That works as well, but it just takes longer, right? So that's virtual machines for these cases might be an option to go. Sorry for the longer backlash. And now going to the question regarding Python and analysis, preprocessing, and what have you. So I think, in my experience, the situation with Python is everything is possible. It's just a question if it has been implemented yet, which is of course not helpful right now to you. So let's focus on preprocessing first. As far as I know, there is unfortunately not a preprocessing, like an entire preprocessing pipeline, whatever, in pure Python. There are aspects of it available. So there, with Nilearn, you can do a lot. You can do some thresholding, detrending, you can do smoothing with Python. That's possible. You can do resampling. A big thing actually is registration, pure Python-based registration, because these image processes behind there are, there's a lot of things, tremendously complicated. And the same holds true for normalization or like other registration things and motion correction, as far as I know. So if you want to have an entire pre-processing thing in Python, right now, I think it's not there. However, I'm rather certain it's possible. Someone just needs to do it. And I guess someone is already working on it, because a lot of people asking these questions, right? And if we come to analysis of fMRI data in Python, I mean, this will be your afternoon, at least in parts, because the second part of the first session will just be focusing on that. How to use Python, that is Nilearn functionality, to analyze fMRI data with the, let's say, classical models you would use in other packages, that is GLMs, for individual and group level analysis. So we're gonna go through that. And that's just for like GLM based stuff, but there's a lot of other packages also dedicated for, let's say, encoding models. We will talk about machine learning later. So once you have to process data, everything beyond that, Python's got your back, I would say. And in the first session, we're going to talk about PyBIDS and statistical analysis of fMRI data. And the first notebook we're going to go through is the PyBIDS one. So if you just click on it, as usual, it should open up. And what this notebook will do is show you how to use the Python package called PyBIDS to interact with BIDS compatible valid data sets, so that you can automatically extract metadata, to automatically get a list of subjects, tasks, query. That's all in there. So once again, here the functionality and goal of BIDS to be human and machine readable really comes in super handy. And this is what PyBIDS is doing. Basically preventing you from adapting your code and scripts, what have you, to your specific structure for the data set, but just having one module that expects a BIDS confirmed data set, because it's highly standardized, that you can then use to get all kind of data out of that and query it. So it's a rather short notebook, as you can see here. We're just going to go through some of the major parts and topics in there, and what you can do with PyBIDS. And as I would say, we just give it 15 minutes, and then we go through with that together, just outlining some important points. So everyone, I think that's the time for that. As you could tell, this notebook was shorter than most of the notebooks we got through like that so far. And to just give you a quick run through and maybe just outline important points. Also for the case you just did not go through all of it, which is of course fine. PyBIDS again is a module to interact with in various ways with BIDS compatible data set. So at the core, you generate this BIDS layout where you basically just provide a path to your BIDS compatible data set. And once you have that, with that layout, you can basically do everything there is when it comes to like querying the data set or also like interacting with it. So you can get like you get very general information. You can get like the number of files, what files are in your data set. You can return specific file names, and sorry, you can get the subjects in the data sets, your available tasks, the different entities that are in your data set. There are different levels of information and how you can specify unique parts of your data set. That's all in there. You can also filter files by certain entities. So if you want to get just one subject and only the imaging data from the functional acquisition type, and you can return the file name, you would do it like this. You can also filter your data and query it by metadata. So you can assess all data that has a certain characteristics and attributes, such as the sample frequency or the acquisition type. And there's a lot of other return values you can interact with. So basically everything that's part of the bit specification, you can put here in terms of querying a data set with Python. You can also generate bits files and interact with those. So it's just a more detailed level here. You can like easily transform it to data frames for easy inspection. Also, like if you want to save it as a data frame, that's no problem. It also allows file name parsing and even path construction. Let's say if you want to include data that might be not bits compatible, but you want to have it as bitsy as possible, or if you want to work with derivatives that are not yet fully supported or part of the common derivatives, that's also something you can do with PyBIDS. Again, getting the layout in a data frame, which enables you a nice overview. You can also include bits validator, as we talked about yesterday. We went quickly through the web version, and here you see an example for the Python. And a new cool thing is the report generation, because if you have a standardized vocabulary and terms for all these aspects of your experiment and the data you have, it's actually easy to generate reports from that. Automated reports. So, and you might have already seen this. fMRI Prep does this for the entire pre-processing pipeline, but also here in PyBIDS, you can do that. And there's a lot of warnings. We will ignore that for the time being. What you can do basically is you can write the data acquisition session of your publication with PyBIDS, and that you just query that, generate a report, and it fills it up with all the information you have. And having standardized data acquisition and, for example, also pre-processing parts in publication makes it way easier to query those things, to also maybe conduct meta-analysis. You can expect what you're looking for. You have the same terms for the same things, which is not given at the moment. So all of these things come in very handy. And this is just one more aspect of how, and the ecosystem around it can ease up your scientific life. And maybe for just briefly talking about how you would use that. So if you are running your pre-processing, your analysis and what have you, you don't have to specify like paths and file names, different variables and whatnot. You can just use PyBIDS for that and query and pass the output through whatever you're interested in terms of your analysis. So this is where it would come in handy, the PyBIDS module. Or as I said before, if you want to write derivatives, you can generate those paths and file names also. Let me quickly check the Slido. Nope, no questions. And in that case, we're gonna continue with the second notebook of this session called Statistical Analysis of fMRI Data. Again, we click on it, depending on your machine, might take a while to open up or not. Here we go. So, and the thing we have to start with here is, unfortunately, a disclaimer. So we started incorporating functional analysis, statistical analysis of functional fMRI data in Python, I think actually just last year, to be honest, like in the iteration of this workshop we gave last year. And back then we used this module and a package called NiStats, which still exists to some extent, but it's archived because it was merged into Nilearn and the Nilearn GMM functionality, or the Nilearn stats module, and how we would call it. So NiStats is archived and it's merged in there. And Nilearn will, in the new release of Nilearn, that should be coming out basically any second or minute, definitely this year. This will be the first version of Nilearn. I think it's 0.7 that will have this functionality included. So in order to show you that and not rely on the archived NiStats package, we included the version of Nilearn that is not the release version. It's going to be a release version, but a working version that's currently on GitHub. We talked with the Nilearn folks if we can do this and if it should be a good idea. And they said there might be a chance, and this is what we also wrote here, that some smaller aspects, just how certain arguments are named or functions, might change. most likely not. And that the bigger concepts and classes and objects and everything there is, those things should remain as we have it here in the example. So take it with a tiny grain of salt, and just to be sure, if you want to use it and the Nilearn version is out, just to cross-check what's there. But again, they have an amazing documentation with awesome examples there, so there's no problem. And I think this might actually be the first workshop or public demonstration of this new functionality in Nilearn, as far as I know. So I hope, we hope you find it as cool as we do. And basically what it's all about is, as the name suggests, how to conduct general linear models and analyze your functional MRI data with that in Nilearn. And it goes through individual level statistics, how to set up your model, how to run it, how to access certain aspects of your model, also evaluate it, and then goes to the group level step. And the last bit we included is how, once more, we can make use of bits in terms of these functionality for a more automated analysis. So for this notebook, I would say we give it half an hour, and then we're going to go through it again. So everyone, I think that's the time for this notebook and section. And while people are coming back here, reorienting, just a brief recap. So this was all about how to conduct statistical analysis of fMRI data in Python using the new GLM stats functionality in Nilearn. And I assume while going through this notebook, you recognize that the steps here are comparable to any other software package that does GLM analysis on fMRI data. It works basically in the same way. So after briefly inspecting our data, the first thing we need to do is to, or we can do, is to specify our experimental paradigm, indicating what kind of conditions we had, when they appeared, for how long, as you would do in any other software package analysis, right? We set it up here. BIDS again makes it easy through the events file to get this information in a standardized format that we can also read with the majority of software that's out there. And then when it actually comes to performing the GLM analysis, we use the functionality and object first level model. And as you check within this cell, it has a lot of arguments you can set. And I think that's comparable to, let's say, SPM or FSL functionality. And one thing we need to access here, for example, is the TR of our experiment. But we can also define the noise model, the HF model, of course, the drift model, the high-pass filter, and the signal scaling, all of these aspects. Comparable to what we did yesterday in the functional connectivity analysis, of course, there are confounds we need to account for in our model. And in GLM analysis, this usually includes the motion parameters you obtain during realignment, but more and more people also starting to incorporate other types of confounds on a more standardized basis. And here again, fMRI prep comes in very handy as it computes a versatile set of confounds reflecting the different aspects of your signal. So for example, you have a signal from the white matter, your global signal, dwarfs, you have parameter displacement, core, temporal, and atomical components. So as also outlined in the fMRI prep documentation, it might be not a good idea, especially if you also include ICA components here, to use all of these in your GLM, because it will most likely lead to rank deficiency, and your GLM can either not be estimated at all, or will just lead to basically a bunch of nonsense, because all of the things are highly, not all of these, but like sets of these confounds are correlated with one another. So you don't have to take, no one would suggest that, I think, all 184, all 24 or even more confounds. And that's why here we restricted to a bunch of them. And then basically we just set our fMRI image, our events, and our confounds, and then we can already fit our GLM that we set up and defined a step before. And we can also investigate our design metrics and train it here. Again, that's old news to you. If you are working with statistical analysis and fMRI data, it's just a design metrics you would see in other software packages as well, but we get the same amount of information here. We can also investigate the expected responses for a certain condition. And then basically what we always want to do, of course, is detect voxels with significant effects. And here we are interested, for example, because in this test, people were moving either their finger, foot, or lips in investigating these responses. So we set the contrast vectors and then can also plot the contrast metrics to be sure that we defined it in the correct way. One cool functionality here, which is not, I think, a standard way of operation or included, at least in tutorials for other toolboxes, is that you can compute different kinds of maps. So mostly, as far as I know, the other software packages are concerned with contrast maps, and then you put them into like for analysis, like group level or what have you. And here, focusing on effect maps and C maps and different kinds of maps is a nice way to approach these things, because it also tells you a lot about and teaches you a lot about data and estimating these models and what you actually get out of that. Then after computing our contrast, we can of course plot it using Nilearn again and different styles. And we can of course also include thresholding, because most likely you just don't want to work with unthresholded images for most cases, depending on the analysis, of course. But at some point in your analysis, you want to apply a threshold. And we can, of course, do this with nice Nilearn GLM stats functionality as well. And you can apply different types of thresholding, different multiple comparison corrections. You can also restrict it to a certain cluster size. That's all in there. You can even get information about certain peaks and peak clusters in your data using the reporting functionality, and can save that for future use. For example, if you want to extract maybe beta patterns out of that, or maybe want to use that for connectivity analysis. We also include an example from using Atlas Reader. That's a package Michael, a bunch of friends, and I were working on that basically also does that, but has a bit more functionality to it, because you can use different atlases here and get a bit more information, and automatically also computes graphics for you. An amazing thing that was introduced within this module is the report function. So you can get a report for a certain condition in your design or in your experiment design, where you can get all the model details, you get your design metrics, you get the contrast you're interested in, the mask that was used for estimating your model, the statistical maps, the contrast plot, and the cluster table, and all these characters that was defined. So that's very cool and super handy to give you an overview, a nice summary of your contrast there. We can, of course, also perform an F-test, and evaluating models, in my opinion, was never as easy as with Nilearn and GLM functionality. So we can, of course, just for a few P coordinates, for example, we can check our model residuals and plot them, how they look and how they are distributed. We can check our predicted and actual time series for our peak voxels, which is also very interesting and important to assess and see. And we can even get our R-squared super easy to check the total amount of variance explained through our GLM and plot that. Going into group level statistics, basically the idea is, as again, any other software package, you would just conduct all of these steps for all subjects you want to analyze, compute the corresponding C maps, contrast maps. So we'll put it here in this little for loop. And then we define a group model where we at first gather all of our maps, define the design metrics, and we just want to compute a one sample t-test. Therefore, it's just 1 times the number of subjects we have. We define our second level model that basically works comparable to a first level model. We provide our C maps and our design metrics input, fit it, compute our contrast type, and there we go. Already have that. So just a few steps with your Python functionality, and as you could tell, it should be very fast. Also, if you have a rather slow machine, you can run these analysis. And of course, it's not only possible to conduct a one-sample t-test, but of course, paired t-test, two-sample t-test, different f-tests, multiple comparison corrections we talked about, that's all in there. And to show you a nice gimmick and feature here, and as spoiled before, we can actually, again, make use of the standardized BIDS data set. Because instead of defining all these things as we did above, we can use the function first level from BIDS, which automatically gathers the models, model run images, the events, and the confounds from a BIDS data set. So you just define your BIDS data directory, the task you want to analyze, the space you have your preprocessed data in, and the derivatives folder where your preprocessed data houses. You provide this information, and you can set all the model information you want to do here, just STR, noise level, noise model, HRF model, as we did before. And then from that, the function gathers all information necessary to run the model. And we just evaluate here, check that it's all working as expected. So we get our run images, we get our confounds, we get our events. And then just within this little for loop here, we just iterate over all these information we get out per participant and fit our model, set it up, and compute our contrast. And then we have our maps per subject. So it's just very easy. And also checking our design metrics again, this all looks good. Contrast metrics as well. And now the cool thing is, instead of gathering all the images we just computed, we can just provide the fitted models as an input for our second level model, for our group level model. So we don't have to gather the Z maps as we did before, but just say, here are the models we fitted on the individual level, take all of them, and now we compute a second level model based on top of that. And then we can compute our contrast again as we did before and plot it. So as you can see, it gets easier, more standardized, straightforward, with a lot of information and things you can do, which is amazing. And that's the first primer on how to do GLM analysis using Nilearn. And if there are no questions, let me go to the, oh yeah, we have a question. That's a good one. Can you perform cluster-wise statistical thresholding as opposed to giving the cluster extent threshold? That's a classic question, but it's a good question though. So these things, as far as I know, are not implemented yet when you talk about Nilearn GLM analysis, but I'm rather certain they will be there, because a lot of people are, of course, interested in applying this type of thresholding.
Well, actually, to take over, this kind of feature is implemented in Nipype since almost 8 years already or so. So I'm using it a lot. So this cluster-wise thresholding is possible with Nipype framework. You don't need to have it in a Nipype workflow. You can just take this one object. So you would do from Nipype, I think models or something like that. You would just take this one package and you can run that directly in your data. And that is possible.
That's it. There you go. Okay. And I think there's no other question. And for the next part, which is just saying one, multivariate analysis using searchlight and deep learning, I'm going to hand over to Michael again, and then we will see each other again for the last part.
So yeah, as just introduced, we have 3 notebooks here, but don't worry, the key notebook that I would love you to see is this one in the middle. And so this whole section goes about how you could use machine learning, and in particular multivariate pattern analysis to analyze your data. And just as a quick pointer to a great paper that was written by Mur, Bandettini, and Krieges-Korte, I will send the link afterwards. So this paper has a nice general introduction to the domain of MVPA, of revealing representational content. And so just to go to one of these nice figures, to explain the difference between such a pattern analysis in contrast to an activation-based analysis. So what Peer was just showing was looking for contrast differences. So if you have finger tapping or foot movement or something else, what is the general activation differences between those two maps? And is this difference significant? So that would be kind of symbolized in this kind of framework. Whereas the pattern information, and I quickly go to the next figure here, the pattern information looks for specific patterns within a specific, certain region. So if we have, for example, now, well, this example is now an auditory example. So you would have a stimuli Ra and a stimuli La, which is very similar. So they would hopefully or most likely create the same activation load within a particular region. So the general activity level would be the same. And so there's not possible with these activation-based analysis to find the difference between these two stimuli. But if you, for example, would look at the pattern within, in this case, the voxels, if they have a very distinct pattern, they would lead to clearly separable patterns. So patterns that can be separated, that can be classified. And so the interpretation here is that they activate a different representation of these stimuli, and this different representation are expressed in different in characteristic patterns. While they might lead to same activation, these patterns are the ones that we're looking for. And so, yeah, this paper highly to recommend. I will send it in the Zoom link quickly. And that's also what we want to look at in this section. And so to prepare something for a workshop that works nicely, I looked for a data set that has very strong differences that would also already work as an activation-based analysis. But what I found was a data set from Zhang et al. With 84 subjects. They were doing resting state, and so they had once everybody of these 84 subjects doing resting state with eye closed, and once resting state with eye open. And you can already see here, just by a simple GIF, you can see, of course, the open effect has already eye motion and some other things. But what I wanted to use here, and that's why I had this preparation notebook created, is I wanted to have a data set where I can quickly get two classes that hopefully should be easy separable. And so you don't need to go through this notebook. I will very briefly summarize it. And as in previous instances, I've used Nilearn and other tools to clean it. So I got this data set. I already prepared everything in the background, but I got the original data set. I looked at the time course. I saw there's a small trend going upwards. So I decided to detrend it and to set score it, so to standardize it. I used a mask to specify the regions of the brain and the eye. The eye, again, here is just as a showcase because, as we saw above, the eye movement is very distinct. So this obviously for any kind of neuroimaging analysis doesn't make sense, except if you're studying the eye itself. And do fMRI on the eye. So what I did is I created these masks, I resampled them to the functional space, I applied this mask to, so here's the mask symbolized on top of the anatomy, and then I have applied this mask on the functional images, and I stored all of that in a huge data set. And this huge data set, to get a bit of information hopefully out of this, I was taking 100 volumes, so we have 100 volumes of each subject with eyes open, 100 volumes of each subject with eyes closed. And I always computed the standard deviation over 25% of this resting state. And so again, this data set is not meaningful per se. It was just one way to quickly create a big data set that we can use for the analysis. And so all of that for all subjects, for all open and eyes closed situations, were stored in a file that is stored under this location, which is then also used in the second notebook. So if you click here on the prediction with Nilearn notebook afterwards, you will get to this one. And so this is the notebook that I would love that you would go through for the next about 20 minutes. But I quickly wanted to introduce you to a few things here and to set the framework. So this one is a notebook that is heavily influenced and inspired by the Nilearn tutorials. And if you haven't done so yet, I can highly recommend that you take a look at the Nilearn homepage. So if I go to the main homepage here, that's how you get on the Nilearn homepage. And they have here nice examples and user guides. And so if I click on the examples, you see tutorial examples, you see some plotting things, some visualizations of brain images. So you have many different things here, the surface plots, decoding. So also part of it is here. So I recommend highly functional connectivity, that what we saw yesterday. I recommend highly to once go through this a bit and look at the capabilities of Nilearn a bit closer. But also in these in the user guide section, they have a lot of things of how to decode and use MVPA, and that's also what we will see now. How to do functional connectivity, how to plot brain, different versions. So this homepage is really, really powerful, and I recommend to look at it. But as a second disclaimer to this small notebook, this is not an introduction to machine learning. That's not possible in this scope, and it is it would need to be a separate workshop or a more detailed introduction to many of the concepts. So many of the things that you see in here might be unfamiliar for you. I will try to explain them and their relevance afterwards when I summarize it a bit. But it should show you how rather shortly or in a compact way you can create such a MVPA analysis. The second disclaimer here also indicates that it's not a blueprint for your study. It perhaps covers 80–90% of what you need to do, but there's always a bit more advanced things that you need to consider to have scientific results. But we will see that in just a bit. But to introduce you directly a bit to the beginning part, we are using these prepared data set, machine learning data set, that has now a spatial dimension X and Y and Z of these many voxels in the 3 directions. Each of them have a voxel a resolution in 4 millimeters. And here I've included 384 different volumes. And so these 384, to do the calculation very quick, it is eyes open, eyes closed for 48 subjects, 84 subject, no, 48. And each of them has 4 images, so 25%, 25, 25, and 25. And so that leads to the number of 384. So I have here, half of them are eyes open subjects, the other one is eyes open, closed, eyes closed subjects, the standard deviation of them. And so that's what the data set is. And to use it, I wanted to create 3 different masks that we will use in just a bit. So if we look at the data on the average data, quickly plot it here. So this one is now, if we take all the voxels that we include in this analysis, again, we have the brain and we have the eye. And in later stages, we want to also, for example, are curious, okay, how can we use the pattern now just in the eye or in the whole brain? Or, and for this, I've used something that Pierre has hinted before, the Atlas Reader. I used the Atlas Reader toolbox that Pierre, me, and others were involved to extract the Harvard-Oxford Atlas from FSL. And I used these different toolboxes to quickly get a mask for the V1 for the primary visual cortex and for A1 for the primary auditory cortex. And that's what the next few lines of codes are doing. So we don't need to go into detail what is happening. It's again using Nilearn mean function, Nilearn math function, and resample and so forth. But here we have a mask for the visual cortex and we have a mask for the auditory cortex. And these are the things that we will use for this machine learning example. And the last but not least bits are the ones that you really need for the machine learning, where we have for each of these initially 384 volumes, we need to have a label. We need to know what's the volume, a volume during eye closed condition or a volume during the eye open condition. And so that's what is stored in this labels parameter, labels list. And additionally, we encoded, usually you would encode which volumes were within one subject, so that you don't have any confounds of leaking one subject into, when you train a model to detect a pattern, that you don't have the same subject also in the testing condition. And so that is kind of what is happening here. We've included directly 8 subjects at once in one class, and that's why this chunks thing is actually indicating in which kind of big chunk one subject is. So we have 6 chunks that we will use for later validation of our models, of our machine learning models. And so the next step, you can just run this part above, this ROI-based decoding, by clicking here, run all above, and then you're already at this stage. And so for the next, let's say for the next 20 minutes, I would recommend to go through these sections. So we have once a section where we want to see, if you look just at A1, primary auditory cortex, primary visual cortex, or the eyes, how well can you decode from the MRI images, from these maps, if a subject had eyes open or closed. And then later on at the bottom, we have then also investigation where you can look at the whole brain at once, where we use a SpaceNet and searchlight approach. And so for the next 20 minutes, go through this notebook. Again, if there are some machine learning concepts that seem foreign, don't worry. I'm happy to highlight them a bit better. Don't hesitate to ask questions, and otherwise we see each other again in 20 minutes. So I think I will continue with summarizing now this part. I hope everybody's slowly getting back. So to recap what the framework was, the setup, we have 384 volumes. Half of them are people during resting state when they had the eyes closed. Half of them were subjects that had the eyes open. And so that could be your data set. You could have numerous volumes or runs or subjects, and you have, for each of these volumes, you have a label. For example, they were exposed to a particular stimuli, or they are of a specific cohort or something like that. And so what you need is, you need to have this 3D volume, and per 3D volume, you need to have a label. And so that was where we left off before. So we have these labels and the chunks. Labels are important to identify which volume has what kind of, and the chunks help us to, in a machine learning sense, to control or to make sure that data of one participant that is used to train a model is not used also to test the model and to validate it. And so the first part that this notebook here highlights is this ROI-based decoding analysis, we've called it. And so let's, for example, take the primary visual cortex. Let's take the data that we have, so eyes open and eyes closed, and let's mask all of this data with this V1 ROI mask, which would then mean it would look something like that. So everything we see here, red and yellow and white, all of these voxels are the voxels we want to use for classification, for training a model. So we train a model to look at characteristics in this pattern, to look at values between all of our subjects, between everybody who has eyes closed. Can this pattern in everybody who has eyes closed, can this one be used to separate them from all other cases where the eyes were open? And so if we take now the V1 region, we need to prepare a training set and a test set. So we have 320 volumes in a training set on which we train a model. We have 64 volumes on a test set on which we validate how stable is our model. So how well can it be generalized on a data set? How well can our model be generalized on a data set that it has never seen? And so that is what happens here. We separate the data on which one we can train and one we can test our model. And then this setup is a standard setup that is used in machine learning. And here we are also using this scikit-learn toolbox, as I've mentioned yesterday, one of the big machine learning toolboxes in Python. I don't want to go into much detail, but what we do here is we say, we have some pre-processing. So we say that the data should be scaled to a right niveau. We say we want to have a linear support vector machine. And so here you could as well just switch to other classifiers, so logistic regression, decision trees, and so forth. So here you have all the flexibility to identify what kind of classifier you want to use for your model predictions, to train your model. And so that's what happens here. And the machine learning part, and that's the key part of machine learning, you give the data to a model, and the model tries to find the right coefficient to do an ideal and optimal prediction. And so these models, to fine-tune the best coefficient combination, they have these hyperparameters. So this one is the parameter C that you can explore and vary. And depending on which C value you set, the better or worse your results might get. So the better or worse your prediction might get. And that is what's happening here. So we explore different C values, we do some other things, and then we fit our model. We fit our model on the training set in V1. We give it the labels of V1. And once this is finished, we might get something like this. And so this plot, again, this is a machine learning domain that is not as quickly to get within 5 minutes of introduction. But in general, what we see here is we've trained a model with different C values. So here at the bottom, these are different model parameters for our prediction. And depending on which model parameter we chose, our accuracy in predicting eyes open or eyes closed reach up to 100% on the training set. But the training set, so the model trained on itself, on the data set itself, and then predicts on this one. So it is understandable that it can reach 100%. What we're interested in is the sweet spot where this so-called validation set, and I'm happy to explain it in a different session, where this score on the validation set is very high. So here, all what we see is we've trained our model and we found a sweet spot of the best model parameters here. And with this model parameter, we have a 75% accuracy of predicting if a person had eyes open or closed, if we look at the pattern within V1. And so if we do the same thing, actually the score is 73% because we used the test set to validate. So this was the initial data set that we separated from our training set. And so we see if we use V1 to train, train a model to see if somebody had eyes open or closed, we reach a 73% accuracy of predicting the right label. And if we do the same thing with A1, so we just change the mask, but otherwise we use exactly the same thing. We have a similar curve, but here right now it's at the 50% niveau, or on the test sets even 45%. This means it is around chance level. So the chance level is 50% of the volumes had eyes open, 50% of the volumes had eyes closed. So here altogether we are around 50%. So this one means that A1, so the primary auditory cortex, cannot be used. The pattern within the primary auditory cortex cannot be used to classify if somebody had eyes open or closed, which is very expected and nice to see. And so what we did now was V1, we had A1, and now let's push it just to the extreme and let's look at the eyes. And if we do the same thing here, we have again this curve where we find the best model parameters. And we see that actually testing our model on the test set, we reach 92% accuracy. And bringing this all together and plotting it nicely, it's what we see here. So if we take these 384 volumes with these labels, if we train a model on part of it and predict on the remaining test set how well it can predict if somebody had eyes open or closed, we see the chance level is at 50%. If we use the pattern in V1, we reach 73%. If we look at A1, we are on chance level. And if we use the eyes, the pattern within the eyes, where we also have the strong movement, we will reach 90% or more of accuracy. And so this is already a nice indication to say that everything seems to go in the right direction. But to do it more scientifically, you would need now to have permutation testing. And that's also what we see in this next section. So what this section does, if I quickly scroll here to the permutation test score, we give it the classifier. So this is the linear classifier, linear support vector machine we trained above. We give it the samples, the labels, everything. And we say for 200 iterations, take the labels, eyes open and eyes closed, and just randomly shuffle them. So meaning that a volume that has eyes closed might be labeled as eyes open, or just a random shuffling of the labels to the volumes that it doesn't make sense anymore. Run it 200 times, and then give us back what the accuracy level can be and so forth. And so if you run that, after the permutation, you can see that this is the distribution of the potential accuracies reached. So on average, we are again at the 50% if the labels are not the right labels that they should be. So we see this distribution is nicely around 50% accuracy. And this red line represents these 73% that we reach with the right labels, with the labels at the right place. And so here with this permutation testing, we can, it's one way to validate that the classification accuracy of 73% seems to have a p-value of 0.005. And so this one is if we use the V1 ROI as we had before. If we use the A1, the same permutation, we see that actually our classification accuracy is exactly in the permutation distribution, meaning in the on chance level. So there's no real value in this classification. P-value is also very high. If we look at the eyes, we have the same pattern as we saw before, and it just supports that this accuracy is actually very high and should be around there. So this was now the steps to use machine learning and classification in this case to predict if somebody had eyes open or closed based on a specific region. But what you can also do is, if you don't know exactly on which regions to look, you can use whole brain approaches. And so Nilearn offers many, but I want to highlight two. So the SpaceNet and the Searchlight. The SpaceNet is something I haven't used much myself, but it is a very powerful tool. And I'm also linking here to the Nilearn page, which then links to the paper. And so the goal of this approach is, if we look at all voxels at once, everything in the brain at once, and we try to fit a coefficient to predict. So if you take the whole pattern in the brain, then if you try to use that to predict if somebody had eyes open or closed, how well does it work? But if you take all of the coefficients, you have too many coefficients in machine learning terms, you're likely bound to overfit. So you should reduce as many as possible. And that's what this SpaceNet approach tries to do. It tries to put as many coefficients as it can find to zero. So to make them zero, to not consider these location. And it tries to only take the relevant voxels and only voxels that are compact in a region. And so that becomes also much clearer that when I show you how the output looks like. So the SpaceNet is a way to find spatial structure, as they call it, in the brain and say, okay, these regions combined with these and these other regions are able to very well predict your labels. And so going briefly through it, this is the setup, how you would call it, how you would train it. And in this regard, the SpaceNet classifier reaches 85% accuracy. And here we see the coefficients. So it puts high coefficients here in the front, in V1, also some up here. And so, as I said before, the SpaceNet tries to have cluster component, cluster coefficient, while trying to reduce a lot of other regions down to zero and not looking at that. And so where in the previous example, we looked at V1, we looked at the eyes, we looked at A1, this one has now the possibility to look at combinations of it. So if V1 is powerful, but the eyes as well, it can use them together. Or if the eyes would be in the other direction, it can use the pattern of these different locations together to get the combined best accuracy. And so this is the SpaceNet, but something that is much more known and also a very powerful tool. Sorry, actually, I wanted to quickly remove these things, is something called Searchlight. And so this Searchlight approach is also the same thing that I've pointed already in the papers that I quickly shared before. What's happening in this regard is it's as similar as the ROI-based decoding, but this time we're looking at very small spheres. So if you look at the whole brain, and if you just take like a golf ball, big sphere, or even much smaller, if you take just voxels within this small sphere, and just take the information, the pattern within this small sphere, how well can you do this classification? And you compute that, and then you can say, okay, on this particular location, just looking at this small sphere, I will reach this accuracy. And the searchlight approach then goes through every step in the brain. It goes through every location, and at every location says, if you take this location with the sphere around it, how well can you predict eyes open or eyes closed in this regard? And so what's happening here, I've chosen a different classifier that works much quicker so that it can be done within a few minutes. We said that the sphere size should be 8 millimeters. This is with respect to the 4 millimeters voxel size. And then we apply, we create this whole object, we run through the whole brain. And what we get out is this accuracy map. And so each of these locations indicate that if we take this location, we would reach about 73% accuracy on just the pattern within these 8 millimeter sphere, or radius 8 millimeters. And so in this plot, the accuracy here is independent from this one here, but because we went through every spot through the brain, we can see that these kind of clusters can emerge. And just to highlight, I thresholded these maps by 60% accuracy. And so to do this right, you would now need to, again, do a permutation testing, figuring out how stable these predictions are, and so forth. But this is the very short summary of the pattern decoding, the MVPA approach. I have also created a TensorFlow Keras notebook that goes in the direction of deep learning. I don't want to cover it to too much detail. It is something that very much goes on the deep learning part, so it's not 100% connected to the Nilearn or Nipype and Python framework. What I want to highlight before we move on to the slides is that, again, it uses the labels and the chunks. So let me actually run it. It takes the same data set as before. We take these labels of eyes open, eye closed. And because of computation time, I decided to do a neural network that uses something that is called convolutional neural network. So it looks at the pattern and the structure within an image. But in this regard, because of computation time, I only look at a 2D image, so only at the top view of the image. And to reduce the whole data set, I only looked at the eyes and V1. That's kind of what we see here, or better here. So we only take these few voxels and look at them and use them for classification. In reality, you would take this in 3 dimensions. You would take a 3D convolutional neural network and try to use a similar approach to a certain degree with the searchlight approach, but a global approach where you train a neural network, an artificial neural network, to find structures and patterns within this framework to get meaningful information out of it. And I've included this part because to highlight how this could be set up with these convolutional networks, how the frameworks would look like, so how these models look like. But this is a full morning or full day other course that could be held. But what I wanted to highlight is perhaps more important, I will go to this overview slide, is that this deep learning part is coming more and more, and Pierre will touch upon it a bit in his slides. There are incredible deep learning models that are currently developed that help with lesion study to directly detect lesion in structural MRI images, that help to segment things like the output of recon all or free service recon all. There are neural networks that can do this within a fraction of a time, still to a not yet best optimal solution. So the segmentation and parcellation is not there yet. But there's a lot of deep learning things coming up more and more that gives very powerful tools in the hands of the researchers who can use them. And so in this regard, the goal was to include a TensorFlow example where you can explore a bit how this new technology looks like and how it eventually then can be used, hopefully, in other projects. And so that would be the end of this section. I saw there's a new question. It's a question about RSA and Searchlight using Nilearn. So I think I will actually hand it over to Peer, as he's more used to that.
Yeah, thanks, Michael, for this very informative, fun session. Regarding the question, though, so right now, I would say no. It's not like an inbuilt functionality that you'd use right off the bench, at least in Nilearn. There is, however, another package regarding machine learning and neuroimaging data, and this is called a PyMVPA. And this package, PyMVPA, has the functionality for running RSA-based search analysis. There's also a package called NL tools, NeuroLearn tools, I think. Mm-hmm. I think this is coming out of, oh my God, somewhere East Coast-ish, one of the Ivy Leagues in the East Coast. I don't know where, maybe Yale, I'm not sure. I gotta look it up though. And I think this also has the functionality to at least do RSA and I guess also Searchlight. Another thing that is currently in development, but never tried it or used it or anything. I think the original RSA people, or like the main group of RSA people, I think they used to be at Cambridge, right? At your institute, and I guess some are still there. But I think they are actually now in the process of converting the famous RSA toolbox from MATLAB to Python. I think this is happening at the moment, but I'm not sure what's the status there.
PyMVPA is still actively being worked on. They have great tools, and I used it already for many other studies. They have very powerful tools, also hyperalignment. So instead of using the structure to realign your images, your functional images, you can also go through function space and do, it's a different concept. It's very strong, but it's exactly we had it in a previous workshop iteration, but because PyMVPA currently works best on Python 2.7 and not really well on 3.7, we've excluded it. But PyMVPA is certainly also a great toolbox to look into. And even though the workshop is called Python, neuroimaging in Python, the Cosmo MVPA in MATLAB is also, so this is pure MATLAB based.
But I think it also runs on Octave, right? I think they are like the examples are actually in Octave. Not sure, I never used it. But like regarding the hyperalignment, functional alignment thing, this is also part in the NL toolbox and a pure Python. This runs on Python 3. What have you. And I also remembered it's from Dartmouth. I'm sorry that I did not have that on top of my head. I think there was another question.
The off-topic one with the model comparisons. Assuming that this one is with the machine learning part, comparing models, I wouldn't know straight away how to do it. The best way would be the question is, how do you want to compare the models? Do you want to see in what way the coefficients are differencing, or do you want to see in which regard the accuracies are different? You could use different classification approaches where you do one single conditions versus all of the conditions, or one single condition versus another condition. So I think it's an in-depth question from my side.
I think you can definitely do it. Depends on the exact implementation would, of course, depend on what you're trying to compare and what's the goal, right? Mm-hmm. But I think the scikit-learn documentation should definitely have sections on that. So just as a quick reminder, what we did yesterday, or what we talked about yesterday. So what we had is, or what we talked about basically is BIDS apps. So how to organize your data, how to standardize it, why is it useful, what can it help you with? And then we checked out self-contained applications that understand BIDS dataset and what they do and how you can use them. And now we're going to jump in and continue with Python packages and then other amazing things. At least, again, disclaimer, according to our experience and opinion. So, is this working? Should be working.
Yeah.
Great. So the first Python module I want to show you, or just briefly mention, is called Nightmare, and it's an amazing Python toolbox for everything meta-analysis. So whatever you want to do with meta-analysis regarding its, it doesn't matter if it's automated annotation, coordinate-based meta-analysis, image-based meta-analysis, functional decoding, working with open databases that are out there, Nightmare is the package for you. It's currently actively being developed. I think there should be something official out soonish, but you can already check the docs that are online. Sorry, here we go. Another thing that's more and more getting important and featured, and more people apply it, is anything related to gradients, brain gradients. And there's an amazing toolbox that came out this year. It's called Brain Space. And this is especially cool, I think, for all MATLAB folks out there, because it has an parallel implementation. So it's a Python module, but it has the same functionality also in a MATLAB toolbox. And what it allows you is basically the creation, alignment of gradients. You can apply various null models for significance testing. You have multi-model data integration, and a lot of amazing plotting functionalities, as you can see here. So if you're interested in trying this very interesting new technique out on your data, I definitely recommend this. And as usual, you got the link to the documentation here, which also includes tutorials and help to get you started. If you are working with multi-echo fMRI data, which also I think is becoming more popular these days, which is a good thing, there is an amazing toolbox called Tedana that is out there, which allows you to do a lot of very important operations analysis regarding multi-echo fMRI, including adaptive mass generation, mono-exponential decay model fits, optimal combination of your echoes, denoising, different decomposition methods, removal of spatial diffuse noise. It also, comparable to other things we've seen before, it provides quality control on confounds and reports and summary statistics, as you can see here. This is the section Mike referred to in his deep learning notebook. This Python module called NoBrainer represents a deep learning framework for 3D image processing. And it supports multiple 3D convolutional models from the current literature and has TensorFlow Keras implementations. And it actually also includes a lot of pre-trained models for brain extraction, segmentation, and different other tasks. And here are just a few examples that you can see. This is the lesion outlining mapping Michael will refer to. You got a T1 weighted image, the model prediction, and the lesion as mapped by an expert. And it also can create, like some of the models included here, can do a free server related task, such as brain mask or different parcellations. So it's becoming a more and more powerful tool, more and more models being added. So we're definitely, if you're interested in 3D, deep learning based 3D image processing, definitely recommend you watch the NoBrainer GitHub space. The link is here. I think Johan mentioned before something about high resolution data, such as 7 Tesla, and also that is supported in Python for the NiRes package. And it supports, as far as I know, I didn't work a lot of it, unfortunately, yet, all of the important things that you might want to address and consider in this kind of special data, including vascular reconstruction, tissue classification, parcellation, co-registration, depth estimation, laminar and surface-related tools. It's built upon the quite famous CBS tools, and I would definitely recommend you check it out if you work with this kind of data. However, there's also another amazing toolbox called Lani. This is unfortunately not in Python, but C. But if you are interested in this kind of field, I would definitely suggest you check out both NiRes and the Lani toolbox. We can make this one short. M&E analysis for neurophysiological data in Python, because you will get 2 days dedicated to this topic, which is fantastic in the next workshop. But just to spoil it a bit, it's basically everything you want to do and more for neurophysiological data. It includes preprocessing, DNA multivariate analysis, encoding, decoding, source estimates, connectivity, time frequency analysis. It has amazing graphics, as you can see here. And it, as of recent iterations, also works nicely with bits and includes informative output. And along the same alley, there's the Nipype module for anything related to diffusion MRI data, which you will also get a dedicated workshop. The organizers did a fantastic job on bringing these topics together. And with that, you can do reconstruction, pre-processing, fiber tracking, streamline analysis, everything you want to do with diffusion data, basically. And it has great interactive visualizations. So, and those are basically the Python models we just want to outline. Again, there are way more out there that you can use for different kind of analysis. There are a lot of Python models coming out for population receptive field modeling, and different kind of encoding analysis. So this is just basically what we're aware about, what we work with, and what based on our experience. And to go a bit further into the more maybe general things, amazing cool things we want to show you, thinking about how to make your workflow more open and reproducible from the beginning. There is a thing called the open brain consent, which goal is basically to make open data sharing a no-brainer for ethics committees. So a while back, this started to provide a resource that people can use. So there are forms up there and templates people can use and adapt for their own study that they can hand in with their ethics application that hopefully helps in enabling open data sharing. Throughout the last year, we also worked hard on including a GDPR edition, which is, I think, not relevant for you in the UK, starting soon. But we also include information regarding anonymization tools and how you can approach these things, also including legal outlets and whatnot. And the link is here, which provides further information and the actual templates. So thinking about the whole in virtualization, Docker situation, how to analyze your data. And I think we had a question before, if you always have to use Docker, or if you can use bare metal installations and how to do it in your own workflow. So if you're ever in a situation where you need to create a container for your own workshop and the things or analysis or what you might want to do, and don't want to go through the rather cumbersome steps and procedure of creating an image and writing this thing from scratch, there's a cool tool called Docker, which is a Docker image that targets the creation of Docker singularity images. And it basically allows you to quickly and reproducibly create containers focusing on neuroimaging analysis. So it's very easy to install, to create a container that includes, let's say, AFNI, ANS, FreeServerFSL, MATLAB compile runtime, Mink tools, mini Conda. So you can also include Python virtualization in there, SPM, and what have you. And it's even true for certain operating systems. You can include different Linux-based systems. It can be Ubuntu, different NeuroDebian, or what have you. And you can basically set up a very complex container as well with Docker quite easily. And they have great examples on the website. So for example, Michael's Nipype tutorial, Docker image is also created with Docker. A nice online resource that brings a lot of these things together is called Giraffe Tools, and it's made by the great Tim and Murik. And I just want to briefly show you that. So Giraffe Tools not only has an amazing website and awesome abbreviations for the tools like Porcupine and Armadillo. Let's focus with Porcupine here for a minute. So what you can do, it's basically a graphical user interface for Nipype workflows. So you can create your own Nipype workflows basically by drag and drop modules in this field here, and then can create inputs and outputs by just connecting dots. And with that, create your workflow. You can set parameters, and different arguments, functions of the node you want to include or your workflow. And the cool thing is, when you have that here, it automatically writes the Nipype code for it that is the workflow, and even then uses Docker to create a Docker image that is able to run your workflow. So it installs all the necessary functionality in there, sets it up, includes your workflow so that you can run the workflow when starting the container. And this is really the next level. This is bringing all these things together and how nicely they integrate with one another. Along this alley, we're going to continue with a cool platform called BrainLive, which allows you to share different code. You can share data, you can discover code or data, and you can even do computations in the cloud. And this is a really cool thing where they have a lot of different analysis pipelines in forms of applications here for alignment, different kind of analysis. So you can see there's a lot of stuff going on there. And you can check out, or you can upload your own data set here, find open data sets, and then you can run these analysis in the cloud or make your analysis re-executable in the cloud for the BrainLive resource. Yet another cloud-based thing that combines a lot of these aspects is NeuroScout, but it does it on a very specific purpose, namely the fast and flexible reanalysis of naturalistic fMRI studies. So you might be aware that there are more and more studies coming out that apply naturalistic stimulation. So people watching movie or listening to long music pieces, and NeuroScout is focused on the analysis of those data sets. So what you can do here, you can browse public analysis, people already did, and you can also create a new one. So what you can do is just create a new analysis. You can take one of these publicly available naturalistic imaging data set, let's say study forest data set from an audiovisual presentation. You use this data set, you go to the next part, and then what you can do is select a set of predictors. And those predictors are basically features from the stimulus that were automatically extracted using different feature libraries that all come together in the Python module called Pliers. And you can include certain set of regressors. So I'm, as mentioned in the beginning, I'm kind of interested in auditory processing and especially in music. So I want to see what's going on with music and maybe animals, and include these predictors. I go next, and you can add a certain set of transformations if you want to have them. The HRF convolutions you apply to your aggressors, just generate dummy contrast. You can also add specific contrast here. And what NeuroScout then does is automatically creating the entire design metrics for that, for the entire data set. So you get, as you can see here, your design metrics, the time course of your predictors, you get the correlation metrics of the predictors, unfortunately currently not working, but you could also get an overview of the data set and you work with it. This is also based on the PyBIDS stats model specification. You can see here, you get all the input. And what you then can do is run the analysis and you can download it. So you can download this entire analysis, and what it does is creates a Docker container. You download the Docker container, you run it, it will get the data, it will get the regressors, run the analysis, and then you can publish it to NeuroScout and check out what's going on there and share it with other people. Very focused on data sharing. There's the Open Neuro platform that allows data sharing for MRI, MEG, EEG, intracranial EEG, and ECOG data. Of course, heavily focused on BIDS. It only allows BIDS compatible data. But as you can see, you by now have the opportunity to check out 436 different public data sets with over 14,000 participants. And it's as easy as going there, searching for data set, let's stick with music. Then you get all the public data sets and you can just download them and work with them. And because they're BIDS, you know how to handle them and can apply your BIDS apps and what have you. Going on the other end of the processing pipelines, if you have your results, NeuroVault is a public repository where you can share unthresholded statistical maps, postulations, and atlases of the brain, where you can, when you go to the website, you can search for a certain term and then get annotations and results for collections that include your search term. And if you click on one of those, just take this one here, you see the unthresholded map. You can explore different views, you can download it, you can get information about the analysis and get all the metadata. So you can use this resource for, let's say, meta-analysis, or if you want to compute effect sizes for your study that you plan to get an idea what's going on. So it's good for power calculations. It's overall a great repository and resource. Another thing that's built on top of this, basically, and focusing on meta-analysis, is NeuroSynth. So NeuroSynth is a platform for large-scale automated synthesis of functional imaging data. And what it does, basically, it has a database of over 14,000 studies. And based on these studies, automatically p-coordinates were extracted, meta-analysis were run, and topic modeling was conducted, and you have over 1,300 terms that you can search in there. So if you go to NeuroSynth, it looks comparable. You can do a meta-analysis based for topics and terms. And if you want to get a meta-analytic map for, once more, music, you type that in, you get the topic, you click on it, and you get your meta-analytic map. And you can even check out all the studies that contributed to this meta-analytic map and their respective loading. Based on this, it also allows to, as you can see here, check out different gene mappings, different locations, or you can decode images. So if you have a statistical map and want to assess in a data-driven way to what kind of process or cognitive term it might relate, you can use the NeuroSynth decoder to find that out. NeuroQuery is also a meta-analytic tool, but it works in a different way. So instead of having predefined terms, NeuroQuery actually accepts arbitrary input. So you can type anything in here. Let's see, what can we do? Music and emotion. Let's see if this works. So it accepts any arbitrary input that you type in here and will generate a meta-analytic map for that, with also the respective loadings, relativity, the weight in the brain rep, and what other terms and features might relate to it. And as you can see here, if you click on one of these terms, you actually see a small brain rep. You can search on Wikipedia, MESH, and if you can also check out the respective publications where you again get the peak coordinates from that. Comparable to NeuroSynth, you can then also download the map and apply for analysis. To focus more on the overarching workflow of scientific projects, DataLad is one of the tools you definitely want to check out. DataLad is super diverse. Everything that is data managing is DataLad. You can discover data just from your terminal. You can search for certain data you're interested in. You can specify search terms. You can download the data. You can publish it as well. It allows, and it's focusing on version controlling your data. So it's not only version control your code anymore, but version control your data. And with that, you can actually, comparable to code, tag a certain process, comment a certain process to your data set, and then this is saved in the log. And then what you can do with that in the end, you have your log where all the analysis you conducted are included, and then basically rerun your entire analysis through this functionality. So if your results get lost, if people want to redo analysis, DataLad is the tool for you because you can redo the entire analysis. You can even include containers and include that functionality in DataLad. So you can also rerun containers and certain versions of containers. When Michael and I started doing these things, we always wanted to include a DataLad tutorial, but we never felt that we are ready for it. And then luckily, Edina Wagner spent a lot of effort and time in creating an incredible resource called the Datalight Handbook that brings you and guides you for all of these different steps and things Datalight can do. So if you're interested in checking that out, highly recommend the handbook for that. Focusing a bit further on reproducibility, there is Repronym, the Center for, or a Center for Reproducible Neuroimaging Computation, which provides you with a lot of information and resources in terms of data and software, but also teaching materials and how to implement standardized description of your data, results and workflows, and make them more reproducible throughout all these different levels. So if you're interested in this topic further, I would definitely recommend to check out the website and the resources they have on there. Now, we talked about analysis and how we can run them, make them more reproducible. One thing that is always, at least in my experience, I think a lot of others as well, a problem is that what you end up with is a PDF. That's all it is. It's a document. There should be the opportunity to make more of your outcomes. They should be more accessible. You should be able to show people more information. You should be able to show them interactive information, maybe provide more details, in-depth code, and combine all of these things together in a living document. And this is exactly the goal of the NeuroLibra project. A repository of interactive neuroscience notebooks. So if you go to their website, you see some example notebooks they created here. For example, also the Introduction to Machine Learning with Nilearn that we did. And basically the idea is you create a document that you can interact with. So it has explanations, it has codes, it's tutorials. So it's basically a Jupyter notebook, but more dedicated specifically for maybe a tutorial, for your publication. And just to give you an example, one of the first ones to come out is this one. It's called the Quest for Measuring Myelin with MRI and Interactive Meta-Analysis, and was set up by an amazing gang of folks that you can see here. And basically they provide further and more in-depth information for their publication, which is out in eLife, if I'm not wrong. So you can actually check out the different things they did here, zoom in, zoom out. This is just an example on how they set up their meta-analytic information. For example, here, we computed effect sizes, and you can see it's all interactive. It provides you with information, what's going on there. You got another map here. So thinking about if you just have one PDF, a document you could go through, or an interactive online resource that you can explore and check out further, I think this is an amazing addition to the scientific workflow and output that we have currently. And actually more and more journals are thinking about supporting this thing. I think eLife might be one of the first ones actually do, but they are very eager to include it on a very regular basis. But other journals as well, such as Aperture. On the leaving the direct application side of things and whatnot, focus a bit more on the community aspects. There's an amazing forum called NeuroStars where you can ask any question related to any neuroimaging, neuroscientific thing. And it's based on the Discourse platform. And for example, if you check once out, you can see it's nicely organized, it's nicely traceable, who answered to what. You can include links, it's markdown based. And it's an overall very supportive community. This is basically where the community meets. You can ask any question, and within hours, usually you get a very helpful, informative answer. And it's just overall a great resource. You can create different topics and tags. If you have any questions regarding any of the neuroimaging stuff you're working with and you run into problems, I highly recommend you go to NeuroStars and check this out further. It also has the advantage that it's not a mailing list. I know a lot of people like mailing lists, but in terms of long-term storage, finding information, assessing information, this mailing list might not be the best idea. And such a thing as a discourse-based forum is definitely more helpful here. Another community thing is the brain hack movement, which is, if you're like thinking about it on different level, I think is actually the reason Michael and I are here right now. The Pybrain movement started a while back, I would say 2012, 13, maybe, or so. It's basically, the idea is people from different backgrounds coming together collaboratively and openly hacking on projects related to brain imaging, to neuroscience, or related things in there. And been quite a ride, and it's been taking off more and more. As you might be aware, OHBM hosts their own OHBN brain hack before each conference, but there's also more and more brain hacks going on and being localized at organized in local venues. And quite often this happens within the Brain Hack Global, which is a week or two each year where the Global Organizing Committee sets up some resources and encourages local sites to conduct their own brain hack event. And also this year, we will conduct a Brain Hack Global, which is from November 13th to December 13th. So if you're thinking about organizing a virtual brain hack this year, please go to the website and check the resources we provided to help you get started with these virtual iteration of events. And if you don't want to host your own local brain hack, you can also just check what else is out there. So because we have a nice schedule here, and currently actually Brain Hack Nostalgia is going on, and you can check all of these different sessions. And usually it should be possible for you to join. So no matter where you are, you can join a brain hack because it's remote. You can join tutorials, you can join talks. So if you're interested in these kind of things and not completely tired of Zoom calls and online meetings and want to have a nice change of what you do with these tools, please be a part of Brain Hack Global. We would really love you to see you there. And within the last 3 slides, I want to outline some important things. So unfortunately, it's an inconvenient truth that academia is not very welcoming to everyone. Despite thinking that we're all doing a good job regarding being open, fair, and supportive, academia has a significant problem when it comes to racism, sexism, and individuals from certain socioeconomic backgrounds. However, luckily, there's more and more being done to create an inclusive and diverse field. And here we want to show you some example initiatives for that. The first being the Women in Neuroscience repository, where when I checked last and when I got this slide, there's over 1,000 profiles from women in neuroscience across different career stages. And it's basically a great opportunity to connect with other women in neuroscience. You can find women in neuroscience for your event. You can check out recommendations, and basically to support this project, sign up, spread the word, and submit the recommendations for individuals here. There's also the Black in Neuro initiative and website, and they're also conducting a conference this year. And I'm unfortunately not sure right now when it's supposed to happen, but it will happen. And it's an overall amazing team. They've done an amazing job when it comes to outreach, raising awareness, and support people. So I would also highly recommend you give this a look and donate and support. And within the last slide, there's a comparable new thing as far as I know. This is called Queer Neuro. And you can use this link here. It's a Google form to sign up. And it's basically right now a database information to connect queer neuroscientists regarding different things. It can be questions, job speaking opportunities, collaboration, and comparable things. A bit OHBM focused, but I think great examples are the OHBM student and postdoc special interest group and the open science interest group, which both have amazing funding and mentoring opportunities to help create a more inclusive and supportive field of neuroimaging. So if you're interested in these things, I would definitely recommend you either become an active part, because every year or every 2 years, there are elections for these groups, or just make use of their fantastic resources. Everyone is over the top, friendly and supportive. So it's just an amazing experience. And some things that we did not put on the slide, and I just found recently, for this year's Neurops, you have an amazing set of workshops focusing these aspects. This is a bit more focused on AI and machine learning, but in my opinion, can serve as a role model of what could also be possible in the field of neuroscience, where you have the queer in AI, Black in AI, Muslims in AI, indigenous in ML. So these are the things that are needed to be done a bit more. And with that, I'm done, and I'm happy to answer any questions. If you have a question, if there's a certain tool that exists for your analysis, certain platforms or resources, just let me know. And I'm rather certain we will be able to find something that fits your needs.
So one question is actually in the Zoom chat. Roma asked, are any pipelines for quantitative susceptibility mapping available? I'm not too familiar. I've found a few links, but
I think within the Nipype, there should be something in the making. Gonna give it a quick search. So there's accessibility to sort correction workflows, but I think somewhere in the online realm, I've seen something for quantitative susceptibility mapping. Don't know it off the top of my head, sorry, but I would assume someone is definitely working on that, maybe within the BrainHack project or something comparable.
Mm-hmm.
Or might it be called QSMI prep, something like that?
No, the QSM, yeah, there are a few,
but it's not there yet. I don't know.
I mean, one of the things I've seen. So perhaps just to quickly give a pointer. Let me see if I can share the screen. That and this. I think you should see. Way too big. That's not the right one. Sorry. Back and forth. Going back to Neurostars, this great forum with many different questions. If you look here for QSM, quantitative susceptibility, I think I've seen before, yeah, here a question. If there's a learning group or some advice, and somebody points here in this chat to the BrainHack Mattermost. And so this is a great link. Mattermost is similar to Slack as a way to interact with your people, with friends, with cohorts, with colleagues. And so if you go into this Mattermost framework, there might be somebody who can give pointers to what else is being worked on with respect to QSM with Python. But so yeah, the Neurostars is certainly a great point to start related to that. Thank you for listening. I see in the chat for thanking us. So thank you very much for listening. We're super excited that we were able to give this workshop. We are, of course, to a certain degree, if the internet doesn't spam us, we're happy to answer any other questions that follow up that come our way.
Yeah, no, I also want to say thank you to all of you for listening, the interesting questions. It's always a blast to give this workshop. It's really nice. And it's also great to see that it's apparently possible, at least to some extent, to conduct this in a virtual setting. So thanks a lot. Thanks a lot to the organizers, Johan and Ola, for setting this up. Fantastic idea. And I hope very helpful to everyone at the Institute.